The final countdown is here. 14 days. That's the entire margin we have left. In exactly 14 days, on December 19th, Lianqianling Ashawu, an ancient visitor older than our sun, older than every mountain range, ocean basin, and living creature that has ever walked this planet, will reach its closest point to Earth. And while you're hearing this right now, the world is already watching. Not metaphorically, literally. Observatories across continents and spacecraft spread through the solar system are locked onto a faint moving target that refuses to settle into an easy explanation. They're tracking 3I, Atlas, as it creeps closer night after night. They're following the shimmer of its two tails, trying to separate what's real from what's optical illusion. What's normal comet behavior from what only looks normal at first glance? And behind all of that observation is one question that has quietly gripped researchers for 5 months, a question that gets harder to ignore. The closer this object gets, is it truly a comet, or is it something we haven't properly named yet? Because here's the uncomfortable reality: the anomalies aren't fading with better data. They're not shrinking into a tidy explanation. If anything, they're accumulating, stacking like evidence on a table while the window to interpret them gets smaller by the day. Once this object swings past Earth and begins its long outbound path toward Jupiter, we're left with only two possibilities. Either we extract answers in real time, or we spend the rest of our lives debating what we failed to capture during the only close pass we're going to get. If you care about these deep, science-focused explorations, if you like, following the story while it's still unfolding, this is the moment to stay close. The next 2 weeks won't be slow. The updates won't be gentle. The timeline is unforgiving. We've been tracking this visitor since July 1st, when the Atlas telescope in Chile first flagged it, an object racing through the outer solar system on a path that didn't belong to anything bound to the sun. By now you already know the headline facts. 3I. Atlas is the third confirmed interstellar object ever observed. Arriving after Oumuamua in 2017 and Borisov in 2019, you know it likely originated beyond our system, possibly from the thick disk of the Milky Way, which means it could be around 7 billion years old. You know it disappeared behind the sun in late October, endured perihelion on October 29th, and emerged on the far side still intact, still active, and still behaving in ways that don't sit perfectly inside the standard comet playbook. But what's changed, and what most people haven't caught up with yet, is what happened in the last 72 hours. On December 4th, Lianqianling Ashawu, a wave of fresh information landed almost all at once, from multiple directions, and it immediately sharpened the debate. NASA released new Hubble images showing 3I Atlas with a clarity we haven't had before. The European Space Agency dropped a teaser image from its JUICE spacecraft, and that single frame ignited arguments that are still bouncing between academic circles and social feeds. At the same time, a newly posted preprint study claims something even more provocative: possible signs of cryovolcanism, ice volcanoes venting from the surface of this ancient wanderer. Pause on that for a second. An object drifting through interstellar cold for billions of years, and then, as it passes through our neighborhood, it appears to stir, to erupt, to show activity that feels almost timed to the moment it becomes easiest for us to observe. That doesn't automatically mean anything. Extraordinary nature is full of surprises, but it does mean we're looking at a phenomenon that could be more complex than just another comet. And the only way we find out is by squeezing every bit of signal out of the days we have left. So let's get practical, because the timeline matters. As of today, December 5th, 3I, Atlas is positioned in Virgo, visible in the pre-dawn sky. For viewers in the northern hemisphere, it's rising earlier and climbing higher each morning. By December 19th, it will have drifted into Leo, sitting almost directly beneath Regulus, a bright, unmistakable marker that can serve as your guide. If you can spot Regulus low in the eastern sky before dawn, you're already close to the right patch of darkness. But manage expectations, you won't see this with the naked eye. This is not a cinematic sky-filling comet. Even at closest approach, 3I, Atlas will remain about 170 million miles from Earth, nearly twice the Earth-Sun distance. The Moon, by comparison, is roughly 250,000 miles away. That means Atlas, at its closest, will still be nearly 700 times farther than the Moon. So yes, there's no threat at all, but it also means you need the right tools to see it. NASA's guidance is clear. A telescope around 30 centimeters, 12 inches aperture gives you a realistic chance. Smaller instruments might catch a faint blur under excellent skies. But for most people, the best option will be joining professional live observations. The Virtual Telescope project in Italy has already announced a live stream on December 19th at 0400 UTC, pointing their remote telescopes directly at 3I Atlas, so anyone can witness the moment without needing a personal observatory. Still, none of that is why you're really here. You're here because something about this object doesn't fully add up. You've heard the whispers about its behavior, about patterns, about inconsistencies that make even cautious people lean forward. And the honest truth is, some of those questions are worth placing on the table carefully, without sensationalism, but without pretending they don't exist. So let's begin where the unease often begins: the trajectory. 3I. Atlas is moving in unusually close alignment with the ecliptic plane, the same flat corridor where the planets orbit the Sun. That's not impossible. Random arrivals can line up. Coincidence is a real force in a big universe, but the ecliptic is also the busiest, most gravitationally structured zone of our system, the region where encounters, perturbations, and observation opportunities concentrate. And when the trajectory is placed alongside everything else, its survival through perihelion, the evolving activity, the recent imaging, the cryovolcanism claim, the story stops looking like one odd detail and starts looking like a cluster of details, not proof of anything beyond nature, but enough to justify the intensity of the global attention right now. Because in 14 days, the moment passes, and whatever 3I, Atlas truly is, ordinary or extraordinary, we don't get a second chance at this close approach. And this is where the geometry stops being a footnote and starts feeling like a pattern. Early calculations suggested that the odds of a random interstellar body arriving along this specific angle so cleanly lined up with our system's primary orbital plane were on the order of 1 in 500. Unlikely, but not impossible. A single weird roll of the cosmic dice doesn't mean much. Then the second detail emerged. As 3I, Atlas continued inbound, analysts realized its path wasn't just near the ecliptic. It threaded the inner solar system with a kind of precision that made people sit up straighter. It passed uncomfortably close to Mars, then Venus, and it's on track to swing toward Jupiter at a distance that lines up almost perfectly with Jupiter's hill radius, that invisible gravitational boundary where Jupiter can, under the right conditions, hold onto moons and capture objects. It's the border of Jupiter's dominion, the place where the planet's pull begins to win. And when you stack those alignments together, angle, corridor, planetary proximity, and the Jupiter approach, some researchers estimate the combined odds of all of it happening by chance at roughly 1 in 20,000. Now, does that prove anything? No, it can't. Probability is not a verdict. It's a way of describing surprise. Improbable things happen constantly. Someone wins the lottery, even though the odds are absurd. But here's the difference: lottery odds reset every drawing. This doesn't. This is one object, one trajectory, one sequence of events piling onto itself. And when the improbabilities start clustering, the only intellectually honest move isn't panic, it's attention. It's asking better questions instead of forcing quick answers. Harvard astrophysicist Avi Loeb has been one of the loudest voices urging that kind of attention. Since the earliest weeks of observation, he's been cataloguing the things that don't neatly match our expectations, and as of this week, his running total has reached 13 distinct anomalies associated with 3I, Atlas. 13 points where the story refuses to be simple. Over the course of this documentary, we're going to walk through them carefully one by one, because each one matters in a different way. But to understand why the debate is getting sharper, you should know what that list includes. It includes the reports of an unusual chemical signature, with significantly more nickel than iron compared to what many would expect from a typical cometary body. It includes the strange presence of an anti-tail, a feature that appears to point toward the sun, not away from it, as if the object is pushing against the visual intuition we've built from centuries of comet watching. It includes the discussion around a non-gravitational acceleration near perihelion, motion that cannot be fully accounted for by gravity alone, and depending on who you ask, may not be completely explained by outgassing either. Loeb has even proposed what he calls the Loeb scale, a 10-point system meant to rank how anomalous an interstellar object appears. On that scale, 0 is clearly natural, 10 is clearly technological and potentially dangerous. His latest public assessment places 3I, Atlas, at level 4, meaning the anomalies cross into territory that, at least in principle, could overlap with what techno-signature researchers would consider worth attention. And then he said the line that hit like a match in dry grass. Loeb has stated that, in his view, there may be a 30 to 40% chance that 3I Atlas does not have a fully natural origin. Let that sit there for a moment, not as a conclusion, but as a signal of how unusual this situation has become. Because that's not a random internet commentator throwing fuel on a rumor. That's a prominent astrophysicist at one of the world's best-known institutions, publicly assigning roughly a 1 in 3 probability that we might be watching something other than a comet. Now this is critical. None of that is the scientific consensus. The overwhelming majority of astronomers and planetary scientists argue that 3I Atlas is exactly what it appears to be, an ancient interstellar comet. A chunk of ice and rock doing what icy bodies do when they move into stronger sunlight. NASA has said it looks and behaves like a comet. The European Space Agency agrees. Most researchers point to the standard signs, the coma, that diffuse halo of gas and dust around the nucleus, the spectral fingerprints of water vapor, carbon dioxide, and other volatiles. The overall behavior that, while unusual in places, still falls within the broad, messy range of what comets can do when they're active. And they might be completely right. But here's the tension. Here's the quiet reason this story won't die. Consensus has been wrong before. Not often, not casually, but enough times that we've learned not to treat agreement as the same thing as certainty. The history of science is filled with moments when the dominant interpretation held the room until the data refused to cooperate. Continental drift was mocked. Hand-washing in hospitals was ridiculed. Entire models of the cosmos were defended with confidence, until the next observation cut the floor out from under them. Consensus is valuable. It represents the best current synthesis of evidence, but it isn't a guarantee. And when anomalies persist, when they don't evaporate with better measurements but instead sharpen, then the correct response isn't blind belief or blind rejection. It's disciplined curiosity. That's what we're going to do together over the next 2 hours. We're going to look carefully. We're going to separate rumor from measurement, speculation from published data, and pattern finding from genuine signal. We're going to examine every claim, every model, every uncomfortable detail, and every explanation that might resolve this story without reaching for the extraordinary. Because whether 3I Atlas turns out to be a billion-year-old natural comet or something far stranger, one fact remains unchanged. We will never see it again. It's moving too fast to be captured by the sun. After December 19th, it continues outward. It will swing past Jupiter in March of 2026. And then it's gone back into the interstellar dark, back into the deep ocean between stars. This is our only close pass, our only high-quality data set, our only chance to learn what it is while it's still near enough for our instruments to speak clearly. So the question becomes practical and urgent. How do we prepare? What equipment matters and what is hype? What should observers look for that automated surveys might miss? What would count as a red flag for something beyond nature, and what would count as a clean confirmation that it's exactly what mainstream science believes it to be? We're going to answer those questions. But first, we need to talk about the claim that has shifted this story into a new register, the one detail that, if it holds up under scrutiny, could reveal the internal mechanics of this object more clearly than any debate about probability ever could. We need to talk about the ice volcanoes, because in the days after perihelion, after October 29th, researchers began noticing activity that didn't look like a simple, uniform outgassing. They saw structure, directionality, repeating forms. Reports describe spiraling jets, and the preprint claims evidence consistent with cryovolcanic plumes, eruptions not of molten rock, but of volatile ices and gas, venting through fractures like pressure valves in an ancient shell. If those images and interpretations hold, they don't just give us a spectacle, they give us a probe, a way to infer what's under the surface, what kinds of layers, what kinds of internal pressure, what kind of composition can remain dormant for billions of years and then suddenly express itself as the object warms. And if we can understand the jets, if we can map where they emerge, how they evolve, what they carry, then we might finally get the first real clues about what 3I, Atlas, is made of, where it formed, and why. Of all moments in its long cosmic life, it chose this passage through our corner of the galaxy to put on such an extraordinary display. So let's go there next. Let's look at the images. Let's talk about the spiral jets. Let's talk about the physics of cryovolcanism and what it would mean to see it on an interstellar visitor. Preparing your eyes for an interstellar guest begins the way most real skywatching begins, quietly. Long before the spectacle, December's pre-dawn hours have a particular kind of hush. If you've ever stepped outside in that thin slice of night before sunrise, breath visible, fingers numb, the world asleep, you know the feeling. Stars hang like they've been nailed in place. The horizon is still black. And for a few minutes, it can feel like the universe is waiting. Over the next 2 weeks, that waiting becomes something else. Because an object that has spent billions of years moving through the empty gulf between stars is about to reach its nearest point to Earth. And if you know the rhythm of the sky, if you prepare with intention, you can see it for yourself. Not as a headline, not as an image reposted 1,000 times, as a real, faint, stubborn smear of ancient light that your own eyes have to work for. But let's be clear, this isn't a walk outside and you'll be amazed event. 3I. Atlas is not a firework. It won't explode into naked eye brilliance. It's closer to a whispered secret than a shout. And that's exactly why it's powerful. It demands effort. It demands patience. And it rewards the people who show up prepared with an experience that feels different, not just astronomical, but personal, like shaking hands with deep time. So here's how you prepare, step by step, without wasting your one good chance. 1. Timing is everything and it's not negotiable. Right now. 3. Atlas is a morning object, and it will remain one through closest approach. That means you're working in the hours before dawn, when the sky is still dark enough to give you contrast, and the object is high enough above the eastern horizon to avoid being drowned in haze. A good rule: aim to be outside at least 2 hours before sunrise. That window, when the sky is fully dark but the comet has climbed, will usually fall somewhere around 3:00 to 5:30 a.m. local time for many Northern Hemisphere observers. Yes, that means an alarm. Yes, that means sleep sacrificed. But consider what you're waking up for, a traveler that formed around a star you will never see, possibly before our sun even existed. You're not just observing a comet, you're watching a fragment of another system's history pass through ours briefly, close enough to matter. 2. NASA's aperture guideline is real, but not the whole story. You've heard the baseline recommendation: a telescope around 30 centimeters, 12 inches, gives you a reliable shot. That's good advice, especially for average skies. But the reality is more nuanced, and frankly more hopeful. If you have an 8-10 inch telescope, 20-25 centimeters You absolutely have a chance under truly dark skies, especially if you're comfortable hunting faint targets and you know exactly where to point. In an Unter under a clean, dark sky. 3i, Atlas may show up as a dim, fuzzy patch, more presence than detail, but unmistakably there once you lock onto it. If you have a 12-inch under heavy light pollution, you may still struggle, because aperture helps, but it cannot fully compensate for a bright sky. Contrast is king, which brings us to the factor that matters more than your equipment. 3. Your observing sight will make or break the entire attempt. If you do one thing correctly, make it this. Don't wait until the night before. Scout now. Drive out. Look east. Actually stand where you plan to observe and ask practical questions. Is the eastern horizon clear? Or will trees and buildings block the low sky? Are there streetlights nearby? A single bright light in your peripheral vision can ruin your night vision faster than you think. Is the location safe, legal, and accessible at 4 a.m.? Can you park without becoming the subject of a security call? Remember, in the days leading up to closest approaches, the comet is rising in the east while moving through Virgo into Leo. You want a clean view of that region as it climbs. Use a light pollution map. There are excellent ones available for free, and aim for the darkest reasonable site you can reach. Sometimes even a 30-minute drive away from a major city can completely change what's possible. The sky is not a background, it's your observing medium. And the cleaner it is, the more the universe reveals. 4. If you don't own a big telescope, you're still not out of this. This is where a lot of people give up too early. Don't. There are 3 strong alternatives, and each one can turn "I'll never see it" into "I was there." Option A. Join an organized observing event. Local astronomy clubs are built for moments like this. Many will host public sessions around December 19th, often with access to instruments far larger than most people own. You get big optics, experienced guides, help locating the exact field, and something underrated: shared awe. There's a special feeling in a cold field at 4 a.m. Taking turns at an eyepiece, hearing someone behind you whisper, "I see it," and realizing this is a one-time visitor for all of you. Check. Local planetariums, university astronomy departments, astronomy clubs in your region. Option B. Virtual observation. Don't underestimate it. The Virtual Telescope Project has already announced a live stream for December 19th at 0400 UTC, using remotely operated telescopes in Italy. Watching through a screen isn't the same as freezing under the stars, but it is vastly better than missing the event entirely. And it often gives you a clearer view than your local sky will allow. And there's something strangely modern and beautiful about it, a global audience watching the same interstellar visitor in real time, stitched together by photons and bandwidth. Option C. Smart telescopes, the middle path that changes everything. This is the category that has quietly transformed amateur astronomy in the last few years. Devices like the C-Star S50 and similar smart scopes combine modest optics with automation and stacked imaging. They find targets automatically, track them precisely, stack exposures to reveal faint detail, and yes, multiple observers have already captured 3i Atlas with tools like these. Which proves something important. You don't always need a giant traditional telescope to participate. You need good planning, good sky, and the right workflow. In fact, one of the most interesting side stories of 3i Atlas is that some amateurs working from backyards with smart scopes and patience have produced imagery that looks cleaner and more informative than some early official releases. We will get into that controversy later, because it raises questions not just about optics, but about how information is curated, when it's released, and what gets left out. 5. The most important preparation isn't hardware, it's your eyes. If you've never hunted faint objects before, you're going to want to practice now, not on the main event night. Here's what matters. Dark adaptation. Give your eyes 20-30 minutes away from bright screens and lights. Avoid white light. Use dim red light if you must. Averted vision, faint objects often pop better when you look slightly off to the side. Patience. Your brain needs time to lock in on low contrast targets. Think of it like learning to hear a quiet sound in a noisy room. At first you hear nothing, then suddenly you can't unhear it. And once you see it, you'll understand why people lose sleep for this. Because this isn't just about spotting a faint smudge. It's about participating in a moment of cosmic timing that will not repeat in your lifetime. It's about training your senses to catch something that has been drifting through darkness for ages and is, briefly, passing close enough for human eyes to notice. Now, before we move on, there's one more thing you need to know. Seeing 3I, Atlas, is only the first layer. The deeper layer is what to look for once you've found it, the shape of the coma, the behavior of the tail, any hint of structure, any change night to night. Because if the cryovolcanic claims and the spiral jet reports hold up, then this isn't a static target. It's a changing one, and a changing object is an object that can tell us secrets if we watch it correctly. So, next, let's talk about what to observe once it's in your eyepiece and how even amateurs can contribute meaningful data in the final 14 days. Let me give you concrete sky landmarks you can actually use night by night so this doesn't stay abstract. Where to point your telescope over the next 2 weeks. As of December 5th, 3I, Atlas, sits in Virgo, not far from Zavijava, also known as Beta Virginis. If Virgo isn't a constellation you normally hunt, don't worry. Start with Spica, the bright, unmistakable blue-white star that anchors the constellation. Once you have Spica, work your way upward and north through Virgo's star field. The comet won't look like a star, it will look like a small, soft presence where the star chart says there should be nothing. And you need to keep one key fact in mind: it's moving fast. Not fast like a planet drifting over weeks. Fast like a traveler sliding across the background enough that you can compare sketches from 2 nights and see the difference. By December 12th, it will be pushing toward the Virgo-Leo border, and it will pass near a faint spiral galaxy called NGC 4536. You won't see that galaxy unless you're working with a fairly large telescope under dark skies, so don't treat it like something you're supposed to spot. Think of it as a celestial signpost for people using detailed charts. If your software shows NGC 4536 inches, the field, you're in the right neighborhood. Then comes the moment the world has been circling on calendars: December 19th. 2025 closest approach. That night, 3I, Atlas will be in Leo, sitting almost directly below Regulus, the brightest star in the constellation. Regulus is one of the easiest landmarks in the winter sky. Find the backwards question mark shape Leo's sickle, and Regulus is right there at the base, like a jewel on the lion's chest. If you can locate Regulus, you're not searching the entire sky anymore. You're working within a small patch, a couple of degrees, and that's a hunt you can actually win. For exact positioning on any given night, don't trust vague diagrams. Use a planetarium app and let it do the hard work. The easiest way to get precise coordinates every night: download Stellarium, it's free and remarkably accurate. Or use a reputable mobile sky app that supports comets. Enter the comet designation C 2025 N1, and the software will place it in your sky for your specific location and time. That last part matters. A comet's altitude and angle change based on where you stand on Earth. With the right app, you're not guessing, you're pointing with intent. Now, once you've found it, what will it actually look like? What you'll see at the eyepiece. Right now, 3I, Atlas is hovering around magnitude 11. That puts it far beyond naked eye visibility, but comfortably within reach of moderate amateur telescopes under good conditions. As it closes in, it may brighten a bit, magnitude 10, maybe slightly better in optimal skies, through the eyepiece. Expect this: a small lay, fuzzy patch, soft-edged, not a pinprick, a shape that looks wrong compared to stars, more like breath on glass. Under darker skies, and enough aperture. A hint of coma structure, a subtle brightening toward the center, with larger scopes or long exposure imaging. Perhaps the faint suggestion of a tail, but I need to set expectations the right way. Because people get disappointed for the wrong reason. This will not look like those dramatic comet portraits online. Those images are built layered from many exposures. Stacked, processed, contrast stretched until faint details become visible. That's not deception. That's how astrophotography works. In real time, comets are almost always ghosts. You don't see them instantly, you learn them as your eye adapts. And yet, seeing it live is something a photograph cannot replicate. Because when you look at 3I Atlas, the photons hitting your retina left that object about 15 minutes earlier. That's not ancient starlight from thousands of years ago. That's immediate, direct contact light reflecting off a surface that may have been traveling through interstellar darkness since before the first humans ever stood upright. A faint smudge becomes a doorway when you realize what it is. So don't treat it like a checklist item. Spend time with it. Let your eyes relax into the darkness. Use averted vision. Let the comet come forward in your perception. That's when the experience changes, when your brain stops saying, "I can't see anything," and starts saying, "Wait, yes." There, if you want to photograph it. Here's the practical approach. If you have a DSLR or mirrorless camera and a tracking mount, start with 30-60-second subs at high ISO. Capture a lot of frames enough to stack. Use Deep Sky Stacker or Sequator to combine them. Here's the trick. Most beginners miss track on the comet, not the stars. If you track on the stars, the comet will smear. If you track on the comet stays sharp, and the stars trail, and that trailing can look incredible because it visually proves motion. It turns the image into a statement: this thing is not part of our sky's normal rhythm. It is passing through. If you're using a smart telescope with built-in stacking, your workflow is even simpler. Point, confirm, let it integrate, and watch the target gradually rise out of the noise, like an apparition. Document what you see because it matters more than you think. This isn't just for your own memory. Write down time and date, location, equipment and magnification, sky conditions, transparency, seeing, moonlight, light pollution, what the coma looked like, any hint of tail, direction or structure, brightness compared to nearby stars. That may sound obsessive. It isn't. Amateur observations have repeatedly mattered in comet science, especially when objects behave strangely, change quickly, or show short-lived features that a professional schedule might miss. And with 3I Atlas, the entire story is built on strangely, so pay attention to anything that feels off, anything that changes from night to night, anything that doesn't match what you expected based on the charts and predictions, because a lot of what has fueled the debate around this object didn't begin in a NASA press release. It began in the quiet persistence of observers, people scanning, capturing, comparing, noticing. And that brings us to the part most people came for. Not where to point the telescope, but what refuses to fit once you do. The 13 anomalies. Professor Loeb's latest count is 13. 13 separate features, each small enough to explain away on its own. Each capable of being filed under unusual, but possible if you isolate it. The problem is what happens when you stop isolating them, because patterns don't announce themselves with certainty. They emerge, they accumulate, they begin to lean in one direction. And once you see that lean, you can't unsee it. The most visually arresting anomalies, the ones that triggered the loudest arguments in recent weeks, center on something that, under standard comet physics, should be deeply counterintuitive: an anti-tail, jets that appear to point sunward, spiral structures in the coma that imply rotation behavior. We rarely see documented this clearly. To understand why those details matter, we have to slow down and do what science actually does, not jump to conclusions, but test the shape of the evidence. So in the next section, We're going to unpack the anomalies one by one, starting with the one you can sometimes see in images even before you understand what you're looking at, the anti-tail, and why impossible is a word astronomy has learned to use very carefully. Anomaly number 11 is where the discussion stops feeling like an abstract list and starts feeling like a stress test for the comet model. 11. The non-gravitational acceleration. If 3I, Atlas, were a simple, inert chunk of ice and rock, its motion would be dictated almost entirely by gravity, sun, planets, maybe a tiny nudge from solar radiation pressure. But as it passed through perihelion, careful tracking revealed a small yet measurable deviation from a purely gravitational path. That deviation is not automatically suspicious. In comet science, it's almost expected. When volatiles sublimate, they act like microscopic thrusters, jets of gas, pushing the nucleus in the opposite direction. That's how comets can cheat their predicted orbit. The issue is not that there was non-gravitational acceleration. The issue is how hard it is to make the observed push line up cleanly with what we see, or more precisely, what we don't see. If outgassing is doing the pushing, you'd expect a consistent relationship: measurable jets, measurable thrust, measurable mass loss, predictable orbital deviation, thrust direction correlated with where the sunlight hits. With 3I, Atlas, those correlations feel messy. The acceleration exists, but the smoking gun mechanism keeps slipping out of frame. Again, not impossible. Just another point on the tally that refuses to sit quietly. 12. The hidden window at perihelion. This one is less about physics and more about circumstance. But in science, circumstance matters because it dictates what we can verify. 3I, Atlas, passed closest to the Sun on October 29th. 2.2, and during the most critical hours when heating, outgassing, fragmentation risk, and surface change would be most dramatic, it was effectively masked from our view. Tucked in the sun's glare, it's the cruel irony of cometary observation. The moment when the object is most revealing is often the moment we can observe it least. The perihelion passage becomes a kind of blindfolded experiment. We know something happened. We just don't have a continuous visual record of what changed and when, so what we got instead were before and after snapshots. It went inactive, it came out active, and whatever it did in that hidden window is inferred from the leftovers. That gap matters because it leaves room for interpretation. A single uninterrupted sequence could have settled arguments. Instead, we have to reconstruct the story from fragments, like trying to understand a wildfire by analyzing ash patterns after the flames are gone. 13. The post-perihelion morphology. And now we arrive at the final anomaly on Loeb's list, the one that ties several of the others together. When 3I, Atlas, emerged from perihelion, observers didn't just see the comet again. They saw a coma that looked structured, not just a fuzzy halo, not just a tail, but patterns, features that implied organization, jet activity that appeared persistent rather than random, spiral-like structures within the coma, suggesting rotation, and renewed debate over whether the sunward feature was truly a veillate. Dust, geometry, illusion, or something more persistent, comets can absolutely produce jets. Comets can spin. Comets can create spirals in the coma, as rotating jets sweep through space like a garden sprinkler. That's not the controversy. The controversy is the total profile, the anti-tail behavior, the unusual brightness curve, the strange color, the survival through intense heating, and then the structured aftermath stacked on top of orbital and planetary alignment oddities. Each anomaly can be argued into the natural category, but the combined effect creates a question that won't go away. How many rare but possible traits should one object display before we stop calling it coincidence and start calling it a pattern? That is the real tension here. Not aliens versus comets. Not sensationalism versus skepticism. The tension is something quieter and more uncomfortable. We are watching an object that keeps behaving in ways that are just off-center enough to provoke debate, but not far enough to end it. Now, before anyone runs away with the most extreme interpretation, we have to do something responsible. We have to flip the lens around and ask what a fully natural explanation would actually look like if we tried to build it from the ground up. Because if 3I, Atlas, is natural, and it very likely is, then the anomalies aren't proof of anything artificial. They're clues about an environment we almost never get to sample, a body formed around another star, possibly from an older region of the Milky Way, arriving with chemistry and structure shaped by conditions we haven't modeled well. So next, we're going to take the anomalies and do what scientists actually do. When something doesn't fit perfectly, we'll group them, not as a dramatic countdown, but as categories of behavior: trajectory and timing, composition and surface physics, light, polarization, and dust geometry, activity and propulsion. Because once you group them, a different question appears: more practical, more testable. Which observations over the next 14 days could decisively tip the balance toward unusual comet or something else entirely? And that's where the story becomes urgent again, because December 19th isn't just a date for sky watchers. It's the point where the universe brings this visitor closest to us and then starts taking it away. And this is where the story pivots from odd to operational, because once you accept the premise that we are dealing with a real object moving fast through a narrow observational window, the question stops being, what do people believe, and becomes, what can we actually test right now before it slips out of reach? The acceleration that refuses to be simple. The tracking data around perihelion didn't just show a gentle nudge. It hinted at something with structure, a push with both radial and transverse components. In plain terms, not only a shove away from the sun, but a sideways drift that's harder to fit into the most basic comet thruster picture. Yes, outgassing can do that. Jets are often asymmetric. A nucleus rotates. Sunlight hits one region harder than another. The rocket effect becomes a messy vector sum of vents and spin and seasonal heating. But messy is exactly the point. If the behavior were purely cometary and purely ordinary, you'd expect the mess to average out into something familiar as more data comes in. Instead, the pattern feels like it's becoming more defined rather than more random, as if the comet isn't merely reacting, but behaving. Not intelligently, not deliberately, just consistently enough to make scientists uncomfortable: the spiral signature. Now we arrive at the feature that keeps dragging everyone back into the imagery: the spiral structure in the coma. Comet jets can spiral. If a nucleus is rotating and a jet vents from a fixed region, the plume sweeps around, painting a curved pattern into the expanding gas and dust. That's textbook. What is not textbook, at least according to the claims being circulated, is the suggestion of dual, clockwise spin waves, implying a stability and symmetry that feels more like an engineered spray pattern than a chaotic comet vent. But here's the sober truth we're still translating: limited, noisy images into three-dimensional physics. Perspective can manufacture patterns. Dust dynamics can imitate order. A spiral seen from one angle can look like two spirals when you process the contrast a certain way. And the coma is not a solid thing, it's a changing, turbulent envelope, sculpted by sunlight and solar wind. So this anomaly lives in a dangerous place, highly visual, emotionally persuasive, and scientifically tricky, which makes it powerful and easy to misread. The Jupiter line that feels too clean. Then there's the forward projection, the pass by Jupiter in March 2026, at a distance that coincides with the planet's Hill radius to within a razor-thin margin. On paper, that sounds like a celestial coincidence with a grin. But in the real world, it's a reminder of something deeper. The solar system is not an empty shooting gallery. It's a gravitational machine. Objects that pass through it are bent, steered, and sorted by predictable orbital mechanics. You can pick out special distances after the fact and compute probabilities. But the probabilities depend heavily on what you define as special, and how many special targets you are willing to accept. Still, people fixate on it because it looks like a maneuver, like a trajectory designed with purpose, and even if it isn't, it's exactly the kind of alignment that makes researchers ask, if you wanted to ride the planetary gravity wells efficiently, would your path look much different? The uncomfortable arithmetic. When Loeb talks about less than 1 inch, 10 billion, he's doing something scientists do constantly, but audiences rarely see up close, trying to quantify intuition. And intuition is slippery. Because the anomalies are not guaranteed to be independent, many of them could be symptoms of the same root cause. Composition affects outgassing. Outgassing affects acceleration. Rotation affects jets. Jets affect brightness. Brightness affects size estimates. And so on. Stack them like independent dice rolls, and the odds collapse toward absurdity. Treat them as correlated outcomes of a single weird comet, and the odds inflate toward plausibility. Right now, nobody can do that calculation cleanly, not with only 3 confirmed interstellar objects as reference points. So the only honest thing to say is this: the probability claims are not the proof. The persistence is the proof of why we must keep looking. Because you're right with most mysteries. The longer we observe, the smaller the mystery gets. With 3i, Atlas, every new dataset feels like it adds a footnote instead of closing a chapter. The mainstream counterweight, and this is where the Jason Wright argument matters, not as a dismissal, but as a guardrail. Comets are chaotic. They do not behave like clocks. They behave like active geology wrapped in dust and ice, with vents that clog, explode, shift, and resurrect. They fragment. They spin up. They change color. They fake you out. And an interstellar comet bombarded by cosmic rays for billions of years, thermally cycled in a void colder than anything we can reproduce on Earth, could arrive with surface physics we've never seen before. That explanation is not only reasonable, it is likely. But even Wright's comets, a cat's metaphor, has a boundary. Cats are unpredictable. Yes, but they still obey biology. They still have bones. They still breathe oxygen. They still leave tracks consistent with what they are. So the real scientific question becomes, do these anomalies look like the track marks of a very strange cat, or like something wearing a cat-shaped mask? And that's why the Trojan horse thought experiment keeps resurfacing. Not because it's the default, but because it forces a critical discipline. What would count as evidence against artificiality? And what would count as evidence for it? If we can't answer that, then we're not doing science, we're doing vibes. The next 14 days, the data bottleneck. This is the part that matters most. We are entering the stretch where observation quality peaks. Hubble has reobserved it November, 30%ed. With fresh processing coming through, JWST is slated for additional looks in December, which, if obtained, can reveal ice chemistry and trace species with an authority no Earth instrument can touch. Ground observatories are piling on both, and amateurs are contributing an extraordinary amount of usable imagery and photometry. But the wild card, the one that shifted the tone of the conversation, came from an angle we can't replicate on Earth. A spacecraft already headed to Jupiter. JUICE wasn't supposed to be part of this story. JUICE was built for the moons of Jupiter, not for interstellar visitors. It wasn't launched to chase comets. It wasn't designed to settle philosophical debates. But the universe doesn't care what we planned. Because after perihelion, JUICE had a vantage point that no telescope on Earth could match, a line-of-sight geometry that let it see the coma and tail structure against a different background, through different scattering angles, with different glare constraints. And then ESA released a teaser. 1 image, 1 frame, barely a glimpse. But it was enough, because it appeared to show 2 tails, not 1. And in comet science, a second tail isn't just a visual flourish. It's a diagnostic. A dual-tail comet can mean dust tail plus ion tail, completely natural, or it can indicate abrupt changes in emission, fragmentation, or multiple active sources, or it can reveal geometry that makes the anti-tail illusion suddenly look less like an illusion. That's why the debates erupted. Not because 2 tails are impossible, but because this object keeps presenting explainable features in combinations that don't feel statistically relaxed. Which brings us to the moment the narrative truly changes. Because on December 1st, 2025, a preprint dropped into the scientific archive that did not just interpret the tales. It proposed a mechanism that would make the entire show jets, spirals, and brightness behavior feel less like random venting and more like geology, not rock volcanoes, ice volcanoes, cryovolcanism. And if that claim survives scrutiny, it doesn't just add a 14th curiosity. It offers a single, unifying idea powerful enough to reorganize the whole case file. So now we go there carefully, scientifically, and without letting excitement outrun evidence. What exactly did the preprint claim? What data did it use? And what would cryovolcanism on an interstellar object actually imply about its interior, its history, and the forces waking it up? Now, researchers working with the Joan Oro telescope in Spain had been tracking 3I Atlas with almost obsessive care as it climbed back into view after its closest brush with the sun. Night after night, frame after frame, they watched the coma rebuild and the tail structures sharpen, and then the images began to show something that didn't fit the familiar script. Not a simple fan of dust, not the usual uneven haze, but spiral jets distinct. Repeating corkscrews of gas and debris blooming outward as if the object had turned into a rotating sprinkler. The pattern looked less like ordinary surface steaming and more like cryovolcanism, ice-driven eruptions powered not by molten rock, but by volatile ices abruptly awakened by heat. And the implications are hard to overstate. For most of its existence, 3I Atlas has been drifting through interstellar space near temperatures approaching absolute zero, cold enough that its interior would have remained locked and preserved for epochs longer than our solar system's entire history. A frozen archive, a sealed vault, material expelled from a home system we will never identify, orbiting a star we will never see. And yet here it was, crossing into our neighborhood, and that ancient ice was venting violently, forming structured plumes that looked like geology in motion. The team behind the analysis, led by Yusef Trio Rodriguez, proposed a specific chain of events to explain what the telescope was capturing. As the comet drew inward, sunlight steadily raised the surface temperature. When it crossed the critical threshold where carbon dioxide ice, dry ice, transitions directly from solid to gas, the sublimation didn't just puff off the surface, it began to open pathways into the interior, widening cracks and exploiting weaknesses like pressure finding seams in old stone. Through those newly active fissures, they argue, an oxidizing liquid could have begun moving, percolating through microfractures, meeting metallic grains of iron and nickel sulfides that had been trapped inside the pristine matrix for eons. That contact is not gentle. It is chemically reactive, potentially energetic, and under the right conditions, it can drive explosive outgassing, not a uniform haze, but discrete jets, focused eruptions launching material in narrow streams. And because the nucleus is rotating, those jets don't simply shoot straight out and vanish. They trace curves, they wrap, they layer into the spiral structures that show up in high-resolution imagery patterns shaped by the object's spin, vent, geometry, and internal plumbing. In this picture, what you're seeing is not the whole surface warming at once, but something far more surgical, specific source regions turning on like valves, producing coherent plumes with repeated structure. None of this is completely alien to planetary science. Cryovolcanism exists in our own solar system. Enceladus, Saturn's moon, famously sprays geysers of water ice from fractures near its south pole. Triton, Neptune's moon, shows evidence consistent with nitrogen geysers. Pluto may host cryovolcanic features as well. The key difference is that those bodies are part of our family tree. They formed from the same primordial disk that built our sun and its planets. 3I Atlas did not. It is a foreign relic born around a different star, assembled from a different disk of gas and dust, shaped by a history we can only infer indirectly. And yet it appears to be expressing a form of ice geology that is recognizable, almost familiar, as though the universe is reminding us that physics doesn't change its mind just because the address is different. That leads to two immediate conclusions. First, the basic behavior of ices is universal. The same phase transitions apply across the galaxy. Carbon dioxide ice sublimates when the temperature climbs past the relevant threshold, no matter which star it once orbited. Water ice follows the same thermodynamics, whether it condensed in our protostellar disk or in a nebula half a galaxy away. That's comforting, because it means our toolkit built here still works out there. Second, and more provocative, the spectral work paired with this cryovolcanism study reported something that quietly reframes how we think about alien material. The chemical fingerprints of 3I Atlas, they suggest, resemble those of trans-Neptunian objects, TNOs, frozen bodies beyond Neptune, where solar heating is weak and time moves slowly. Pluto is the celebrity example, but thousands of TNOs have been catalogued. From small shards to dwarf planets. Even more striking, the researchers reported similarities to primitive meteorites, carbonaceous chondrite-type material, often considered among the most ancient and least altered building blocks in our own system. In other words, despite arriving from another star. 3I Atlas may be made of fundamentally familiar ingredients, the same broad categories of ices, rock, and organics we see in the deep freeze outskirts of our own neighborhood. If that holds up, it's not just an interesting coincidence. It suggests the raw materials of planetary systems might be common across the Milky Way, that the starter kit for world's volatile ices, rocky grains, organics may emerge again and again around countless stars. And if the ingredients are widespread, the chemical pathways that can lead toward biology may also be widespread. In that sense, 3I Atlas isn't just a curiosity streaking through the inner solar system. It's a data point in the largest question we ever ask: are we alone? But there is one part of the cryovolcanism story that has unsettled some researchers, not because it screams artificial, but because it feels too orderly to dismiss without a closer look. The spiral jets themselves. When material erupts from a rotating body, the resulting shapes depend on the rotation rate, the ejection speed, and the geometry of the vents. If vents are random and the nucleus is rotating chaotically, as most comets do, you expect irregular, shifting structures. Comet nuclei are famously unstable rotators. Asymmetric outgassing torques them, makes them wobble, tumble, and change spin states unpredictably. Yet what appeared in some processed imagery wasn't purely chaotic. The jets looked coherent, like repeating spirals laid down by a stable, consistent rotation state, and an independent analysis circulated online, produced by amateur astronomers, and shared widely claimed it could identify dual clockwise spin waves within the comet's structure. If that interpretation were confirmed, it would imply a remarkably stable rotation axis and an internal arrangement capable of sustaining consistent venting behavior. However, and this matters, those claims are not settled science. That particular analysis has not been peer-reviewed. The images require substantial processing to reveal faint structure, and processing can introduce artifacts that look like symmetry where none exists. The authors of the cryovolcanism preprint have not endorsed the most dramatic rotational interpretations, and there are natural mechanisms that can produce organized jets, unusual internal geology, vents in favorable locations, or a rotation state that happens to be temporarily steady. But the question remains alive because the evidence remains visible. The images exist. The structures exist in some form, and they sit on top of everything else that has made this visitor so difficult to reduce to a simple category. To visualize what observers are describing, imagine this: a dark, charcoal-coated nucleus several kilometers across its surface, blackened by billions of years of cosmic ray exposure. As it warms, carbon dioxide ice near the surface starts to turn directly to gas. That gas escapes, dragging dust and fine debris with it, building the coma. Beneath the surface, the heating is uneven. Some zones are porous. Some harbor more volatile pockets. Pressure builds until, suddenly, a vent opens, then gas and dust rocket outward at hundreds of meters per second in a focused jet. Now add rotation. That vent swings through space as the nucleus spins, tracing an arc like a rotating sprinkler. Multiple vents create multiple streams. Their paths overlap and braid into complex patterns that only become obvious in long exposures. And if rotation is stable and vents are positioned just right, those patterns can arrange into spirals with a kind of unsettling regularity. So the central question isn't, are spirals impossible? They aren't. The question is, are the spirals we're seeing consistent with a naturally scarred, randomly venting nucleus? Or do they hint at an internal structure that is more organized than we expect from a typical comet? It's too early to answer definitively, and anyone claiming certainty right now is getting ahead of the data. But we can talk about what the next stage should look like, because the object is moving through a short window where the right observations can actually discriminate between possibilities. As 3I Atlas continues to move away from the Sun, its activity should, in theory, decline. Less heating means less sublimation. Jets should weaken. The coma should thin. That's the typical post-perihelion arc. The key word is should. This object has already resisted neat expectations. Its brightness, evolution has been unusual. Its structural integrity has been stubborn. And there is no guarantee the next 2 weeks will behave like a textbook chapter. Researchers are therefore watching for changes tied to temperature thresholds. Different volatiles turn on and off at different distances. As the nucleus cools, the emission profile should evolve, certain species dropping, others becoming relatively more prominent. Shifts in the balance between water production and CO2-driven activity could reveal what's really powering the jets. This is where the James Webb Space Telescope becomes critical. Its infrared instruments can identify molecules with extraordinary precision, building the most detailed chemical inventory yet of an interstellar object. If unusual compounds are present, if the chemistry deviates sharply from what we'd expect, JWST has the capability to expose that. Meanwhile, ground-based observers will keep monitoring the visible structure tail morphology, jet persistence, brightness changes, and any sudden outbursts or fragmentation. And the amateur community, thousands of skilled observers distributed across time zones, adds something professionals cannot replicate: continuous coverage and rapid reporting. In comet science, amateurs have a long record of catching the unexpected first, simply because they are always watching. With so many eyes tracking 3I Atlas as it approaches December 19th, Liantianling Arshawu, the odds of detecting unusual behavior are as high as they're ever going to be. And that brings us to the hardest question, the one people dance around. But that deserves a direct answer. What would actually convince mainstream science that 3I Atlas is not natural? The default assumption is natural origin. And it should be. Extraordinary claims demand extraordinary evidence. So the bar is high, and one of the clearest candidates for crossing that bar would be something nature struggles to fake: a major trajectory change that cannot be attributed to outgassing. If 3I Atlas were to make a sudden, unambiguous maneuver, an actual change in course that cannot be reconciled with outgassing, fragmentation, or any other momentum-conserving natural process that would be the closest thing astronomy ever gets to a courtroom confession. Conservation laws are brutal that way. You can bend them with hidden mass loss, jets, and asymmetric activity, but you can't break them without paying the bill somewhere, short of a trajectory smoking gun. There are other signatures that would force the conversation into entirely new territory. Artificial light emission would be one of them. Radiation that doesn't match reflected sunlight, doesn't match known fluorescence lines, and doesn't behave like normal thermal glow. If the object began emitting in distinct bands, pulsing, or producing spectra incompatible with natural chemistry, it wouldn't be a weird comet anymore. It would be a physics problem. Radio transmission, especially narrowband, Drifting in frequency in a way that tracks the object's motion would be another. That's why facilities like Meerkat in South Africa have already looked. So far, nothing has been detected. And the non-detection sets an upper bound that's often described in blunt terms at that distance. It rules out transmitters with power comparable to everyday consumer devices. But nothing yet is not nothing possible. The searches continue. The strategies evolve. And as the geometry improves and the object brightens, so does our ability to test. And then there's the most cinematic possibility, structural revelation. Something in imaging that looks manufactured, repeating right angles. Smooth, reflective planes. Symmetry too clean to be geology. Realistically, that's the least likely path to certainty simply because of distance. We're not going to get close up. Spacecraft-grade photography here. We're watching from far away through instruments that resolve brightness, spectra, and motion far better than they resolve bolts and panels, which leaves us where most scientific controversies actually live, in the uncomfortable middle ground. The anomalies matter. They can be documented. They can be debated. They can be stress-tested against models. But anomalies are not proof. Because nature is endlessly creative and always has one more escape route, one more parameter you can change, one more uncommon composition you can invoke, one more geometry trick you can try. That is exactly why the debate has been so intense. 3I Atlas behaves almost like a comet, but not quite. It refuses to settle. It keeps offering features that demand explanation. And the closer we look, the more complicated the portrait becomes. And now, layered on top of everything else, we have something new: data arriving from a spacecraft that was never built for this story, yet may end up shaping how we remember it. Because JUICE has given us our first view of 3I Atlas from beyond Earth's orbit. The JUICE revelation and the hidden tales, some of the biggest breakthroughs in science, come from instruments doing side quests. The ** European Space Agency's Jupiter Icy Moons Explorer JUICE ** launched in April 2023 on an 8-year voyage to the Jovian system. Its mission is Europa, Ganymede, and Callisto ice crusts, hidden oceans, and the long, patient search for habitable environments beyond Earth. Nobody designed it to chase interstellar visitors, but the universe doesn't care what's written in your mission proposal. When 3I Atlas was discovered in July 2025, ESA mission planners noticed something extraordinary. JUICE was positioned roughly 60 million kilometers from the comet's trajectory during a critical period when Earth-based telescopes were fighting difficult geometry and solar glare. JUICE wouldn't be close in any human sense. But in astronomical terms, it was a privileged seat, one that offered a clean, unblinking view when our ground-based instruments were forced to squint. So they took it. Between November 2 and November 25, JUICE dedicated time to 3I Atlas, using 5 scientific instruments. Not just cameras, but spectrometers and particle sensors. That matters. Images tell you what it looks like. Spectra tell you what it's made of. Particle sensors tell you what it's shedding into space. Together, they don't just make pretty pictures, they build a physical explanation. But there was a catch. And it's the kind of catch that only space missions can invent. During this phase of the cruise, JUICE is using its main high-gain antenna as a heat shield, protecting the spacecraft from solar radiation. With the high-gain antenna unavailable, JUICE can only transmit through a smaller backup system at drastically reduced data rates. The result is painfully simple. The full dataset won't reach Earth until February 2026. 3 months. 3 months of waiting while the most valuable observations of an interstellar object in history sit on board a spacecraft, compressed into a pipeline that trickles instead of streams. But scientists, being scientists, couldn't resist a preview. So ESA released a teaser, a quarter of a single image from the navigation camera, just a fragment, pulled down first because it was small enough to transmit quickly. The image was taken on November 2, just 2 days before JUICE's closest approach to the comet. Even in that partial frame, the comet immediately did something it has done repeatedly throughout this entire saga. It made the story bigger. 2 tails. The coma is obvious, a bright, concentrated glow suspended in black space. But extending from it are 2 distinct structures. A plasma tail, formed from ionized gas swept into a narrow streamer by the solar wind. A separate dust tail, fainter and differently oriented, made of heavier particles that respond more slowly to radiation pressure. On paper, this is not shocking. Many comets display both an ion tail and a dust tail when conditions and viewing geometry cooperate. The plasma tail tends to be straighter and points almost directly away from the sun. The dust tail is often broader and curves, lagging along the object's orbital path. So why does this matter here? Because in context, the dual tails do 2 important things. First, they confirm high activity at the time JUICE observed it. Not theoretical activity, not inferred brightness curves visible. Structural evidence that the object was outgassing strongly enough to build both tail systems in distinct form just after perihelion. Second, they offer a coming diagnostic jackpot. Once the February 2026 downlink arrives, researchers will be able to separate the story into components. The plasma tail becomes a chemical witness. Different volatiles ionize differently and radiate at characteristic wavelengths. Its spectrum can reveal what ices are turning to gas and how the solar wind is interacting with the coma. The dust tail becomes a forensic record of grain sizes, ejection speeds, and mass loss behavior, exactly the parameters tied to the anti-tail debate and the object's oddly persistent dust structures. And there's a deeper advantage, one that may end up being JUICE's real contribution. JUICE didn't just see 3I Atlas, it saw it from a fundamentally different angle. Everything we observe from Earth is locked to Earth's orbit, one line of sight, one geometry, one perspective. That geometry controls what features are visible, how tails overlap, whether a forward scattering dust fan looks like an anti-tail, and whether a spiral jet looks like a spiral or just a blur. JUICE, positioned about 60 million kilometers away from Earth's viewpoint, provides a second eye, a stereoscopic baseline, and with 2 viewing angles, Earth and JUICE scientists can begin reconstructing the 3-dimensional structure of the coma and tail system rather than guessing from a single projection. For an interstellar object, that is unprecedented. When Oumuamua arrived in 2017, we had a short observing window and no spacecraft positioned to give a second perspective. When Borisov followed in 2019, we had more time, but still only Earth-bound geometry. 3I Atlas is the first interstellar visitor being studied from multiple locations across the solar system during a critical phase of activity. And that means the next step isn't more speculation. It's triangulation. Because once you can model the tails in 3D, once you can separate what's real structure from what's merely perspective, you can start answering the questions that have fueled the controversy from the beginning. Which tail is doing what? Which dust populations are present? Which volatiles dominate the outgassing? And are the features we're arguing about truly unusual or simply revealed to be normal once we stop looking with only one eye? And that brings us to the most important shift in the story. The mystery is no longer just whether 3I Atlas is strange. It's how it is strange, and whether that strangeness is the fingerprint of exotic natural history, or the first clue that we've been asking the wrong question all along. Next, we need to talk about what JUICE can reveal that Earth cannot: the tail, geometry versus the anti-tail, and how a change in vantage point can either collapse an anomaly or upgrade it into something far harder to explain. The scientific payoff from this kind of coordinated campaign is almost impossible to exaggerate. For the first time, we aren't just spotting an interstellar visitor, we're building a 3-dimensional, time-evolving portrait of one. We're watching how it reacts as solar energy penetrates its layers, how its outflow geometry shifts as it rotates, and how its activity rises and falls over months instead of days. Nothing like this existed for Oumuamua. Nothing like this existed for Borisov. With 3I Atlas, we are finally doing interstellar science with something closer to the thoroughness we usually reserve for objects that belong to our own backyard. And yet, even that tiny JUICE teaser, just a fraction of a frame, managed to open new questions instead of closing old ones. On the face of it, the image is straightforward: a bright coma, a plasma tail stretching upward, a dust tail angling away toward the lower left. Clean, readable, almost textbook. But some analysts, people who live and breathe comet morphology, have pointed to faint extensions and subtle structures that don't sit comfortably inside a simple two-tail interpretation. The problem is that faint features are exactly where the line blurs between signal and illusion. Are we looking at processing artifacts, noise shaping itself into meaning, or are those wisps real evidence of jets, fragment debris, transient outbursts, or material shedding in bursts rather than a steady flow? We can't answer that yet. Not responsibly. The full dataset doesn't arrive until February 2026. And until then, even well-intentioned analysis is forced to lean on partial information. The danger is obvious when you only have a sliver. Your mind tries to complete the picture, but what we can say without stepping beyond what the data supports is that JUICE itself described the view with a word that matters: surprised. They expected post-perihelion activity. Yes, they expected a coma. They expected tails. What they didn't expect was the intensity, the brightness of the coma, and the clarity of the tail structure for an object already on the outbound leg, already receding from the sun. That reaction connects directly to one of the anomalies we talked about earlier. 3I Atlas brightened faster than models predicted approaching perihelion, and it has remained brighter than expected afterward. Its light curve refuses to sit neatly inside the templates we've built from decades of solar system comets. There are natural explanations that could account for this, and none of them require anything exotic. A higher fraction of hypervolatile ices, a more porous structure that lets heat propagate deeper, waking up reservoirs that would stay dormant in a less fractured nucleus. A surface chemistry altered by billions of years of cosmic ray bombardment chemistry that might respond to solar heating in ways our models don't fully capture. All plausible, all reasonable, none confirmed. And JUICE wasn't alone in seeing this visitor from an angle Earth couldn't offer. NASA's planetary fleet, scattered across the inner solar system, contributed observations that turned a single viewpoint into something closer to a network. When 3I Atlas passed near Mars, the event became more than a flyby. It became a geometric advantage. The Mars Reconnaissance Orbiter, using its high-resolution camera, captured images as the comet swept past within about 19 million miles of the red planet. The Perseverance rover, sitting on the Martian surface, aimed its cameras upward and photographed an interstellar object in the sky of another world, an image that, even stripped of all scientific context, feels like a line from a future history book. I went to, built to study the Martian atmosphere, gathered spectral information tied to the comet's emissions, another layer of chemistry. Another piece of the puzzle. Add to that the contributions from ESA's ExoMars Trace Gas Orbiter, and the Mars-based measurements did something quietly powerful. They sharpened the comet's trajectory predictions by roughly a factor of 10 compared to Earth-only tracking. That might sound like a technical footnote, but for an interstellar body moving at over 150,000 miles per hour, it's the difference between roughly knowing where it is and precisely knowing where it must be. Small uncertainties today balloon into huge uncertainties weeks from now. And precision matters for one reason above all others. If anything truly unexpected happens, anything that can't be explained by outgassing the sky won't hide it. A refined trajectory is a tripwire. It turns speculation into a test. If 3I Atlas deviates from its predicted path in a way that doesn't match normal non-gravitational acceleration, that deviation will stand out starkly against the tightened error bars. If it performs a maneuver, we'll see it. If it doesn't, that absence is informative too. So far, the motion has behaved within expected tolerances. The non-gravitational acceleration detected around perihelion is consistent with intense cometary activity, messy, asymmetric outflow, producing small but measurable pushes. No impossible course changes. No sudden, unaccounted-for turns. But the window isn't closed yet. And December 19th, 2025, the day of closest approach to Earth, will give us the best opportunity for precise measurements before the visitor slips farther away and the signal weakens. Then comes the long arc of analysis. When the JUICE dataset finally reaches Earth in February 2026, the real work begins, and it won't be fast. High-resolution spectroscopy will be sifted line by line to identify molecules and constrain abundances. Particle measurements will be used to infer dust, grain sizes and distributions. Imaging will be reprocessed, calibrated, and interrogated for every subtle clue about nucleus behavior and coma structure. Comparisons will be made against solar system comets, against Oumuamua, against Borisov, against simulated models of interstellar objects shaped by deep time and cosmic radiation. Papers will appear, arguments will sharpen, rebuttals will follow, understanding will tighten, not in a single leap, but in the slow, grinding way science always moves when it's doing its job properly. And still, even after all that, some questions may remain permanently out of reach. We cannot land on 3I Atlas. We cannot rendezvous. We cannot pivot an intercept mission into existence on short notice for an object that was already racing through the inner system by the time we recognized what it was. By the time the world knew the name, the window for a chase was already gone. We get one chance, a handful of months of observation, concentrated around this brief corridor of proximity. After that, the visitor keeps going. It swings past Jupiter in March 2026 and then disappears back into interstellar darkness, taking whatever secrets remain with it. Which is why what's happening around the official data has become so volatile. Because while researchers do what researchers always do, wait for complete data sets, demand calibration, argue carefully over interpretation, a different storyline has been surging in parallel, driven by fragments, screenshots, compressed images, and half-context claims. And it doesn't just challenge the interpretation of 3I Atlas. It challenges the trust pipeline itself. Who gets believed? Who gets dismissed? And why so many people now feel they have to read the sky through institutions they no longer fully trust. When NASA finally stepped back into the light after 43 days of enforced silence during the government shutdown, the agency didn't just return to work. It returned to a stage that had been filling itself without them. And that's the part people underestimate. A shutdown doesn't pause the universe. It pauses the voice people expect to interpret the universe for them. While NASA's public channels went dark from mid-October through late November, 3I Atlas kept moving. It slipped behind the sun, survived perihelion on October 29th, re-emerged, and continued its approach toward Earth. The object didn't stop being watched. It was watched more than ever by amateurs, by foreign agencies, by private analysts, by anyone with a camera, telescope, or a platform. So when NASA finally announced a press conference for November 19th, the anticipation wasn't simply scientific. It was emotional. It was political. It was cultural. It was the pressure release of a month-long vacuum. People expected the dramatic reveal. They expected the kind of imagery that ends arguments. They expected something that would make everyone, skeptics and believers alike, go quiet. Instead, they got what looked like a fuzzy white dot, and the reaction was instantaneous. Because the images NASA presented, especially the much-hyped view from the Mars Reconnaissance Orbiter's HiRISE camera, didn't feel like NASA. HiRISE has photographed Mars with astonishing clarity. It can pick out objects on the surface smaller than a meter, It produces the kind of detail that makes you forget you're looking at another planet. But 3I Atlas wasn't on Mars. It was 19 million miles away when HiRISE imaged it. And at that distance, physics stops caring about your reputation. A camera designed to map terrain up close does not magically become a super telephoto lens just because the public wants it to. Its power comes from proximity. Take away the proximity, and even the most powerful imaging system ever sent to another planet becomes effectively a modest telescope pointed at a faint target across an ocean of space. That nuance didn't land, or rather, it landed too slowly. Social media did what it always does in that situation. It converted disappointment into suspicion. How could amateurs with backyard gear show tail structure, coma, texture, jet hints, while NASA, with billion-dollar spacecraft, gave the world a blur? Why did independent astrophotographers seem to be beating the agency at its own game? And the question that always arrives when expectations collide with reality: what are they hiding? The controversy spread fast enough to hit mainstream coverage. Articles and threads began comparing amateur images brightened, sharpened, stacked, processed against NASA's preliminary releases, which looked like underwhelming blobs. The contrast created a story that was emotionally irresistible. The small, scrappy outsiders producing clarity while the giant institution offered haze. But the reality, as usual, is less dramatic and far more revealing about how modern science communication breaks. Here's what most people missed. The amateur images being circulated were rarely single exposures. They were often the result of long integration times dozens, sometimes hundreds of frames aligned and stacked, tracked on the comet's motion, then pushed through contrast enhancement and noise reduction pipelines designed specifically for faint, diffuse objects. Amateurs were doing what comet imagers do best, trading immediacy for clarity, time for signal, patience for detail. NASA, on the other hand, was under public pressure to show something now. The press conference wasn't a journal paper. It wasn't a final calibrated release. It was a public moment fast, simplified, compressed, preliminary frames, quickly processed, presented to a world that had been waiting in the dark. That doesn't mean NASA couldn't produce better outputs later. It means what they showed on November 19th wasn't the final product. It was the fastest product, and speed is expensive in a different currency trust, because explanations don't travel as fast as screenshots. If you tell the public this is preliminary, most people still see it as the reveal. If you tell them processing will improve it, they hear we're stalling. If you say this is consistent with a comet, many will interpret that as stop asking questions. That last part mattered more than the pixels. The press conference tone didn't merely underdeliver visually, it overcommitted rhetorically. When Associate Administrator Amit Kshatriya opened with a statement essentially equivalent to "this is a comet," it looks and behaves like a comet, and all evidence points to it being a comet. He was speaking from the mainstream consensus, and in a technical sense, he had solid ground. But rhetorically, it landed like a door closing, not because the statement was necessarily wrong, but because it didn't acknowledge the psychological reality of the moment for 43 days. The public conversation had been driven by uncertainty, amateur discoveries, foreign agency snippets, and Avi Loeb's daily anomaly-focused commentary. In that environment, certainty doesn't sound reassuring, it sounds defensive. And that is where NASA unintentionally lost the room, not through secrecy, through messaging, because even people who fully accept a natural explanation still want to hear the words, "Here's what we know," "Here's what we don't," and "Here's what we're doing next." They want transparency not only about conclusions, but about uncertainty. They want an institution confident enough to say yes. Some of this is strange, and we're treating it seriously. Instead, many viewers heard "case closed," and once a portion of the public believes an institution is trying to close a case too quickly, every imperfect image becomes evidence not of limitations, but of intent. That's how skepticism snowballs. in the age of instant access, not because people are irrational, but because they're pattern matching sometimes correctly, sometimes not, against a long history of institutions over-promising clarity and under-explaining complexity. And here's the uncomfortable twist: Avi Loeb's criticism, while often framed by detractors as sensational, had a sharper target than cover-up. His real point was about posture. He argued that NASA should have emphasized what remains unresolved, rather than speaking as if the story had already been settled. On that level, communication strategy, he wasn't wrong, because the public can forgive blurry images. What it struggles to forgive is being told that curiosity itself is unnecessary. And that brings us to the deeper question: if NASA wasn't hiding a secret, why did so many people feel like it was? The answer has less to do with telescopes and more to do with trust: how it's built, how it's lost, and how easily it fractures when an extraordinary event collides with institutional certainty. Now, let's talk about the phrase you heard repeatedly in those days, sometimes as an accusation, sometimes as a defense: they have better images. Do they? And if they do, when would they release them, and why wouldn't they show them immediately? They didn't show up to be told to stop wondering. They tuned in because they believed NASA would finally show what it had seen: something concrete, something clarifying, something that would shrink the space where speculation thrives. Instead, what unfolded felt less like revelation and more like reassurance by declaration. And that disconnect between what people hoped to witness and what institutions felt safe delivering has become one of the defining tensions of the entire 3i Atlas story. On one side, you have the institutional voice: calm, careful, contained. NASA repeatedly foregrounds what is established, what is statistically likely, what fits within familiar comet behavior. It emphasizes safety. It emphasizes precedent. It emphasizes control. There's comfort in that approach, especially when millions of people are watching, and the last thing an agency wants is panic or sensationalism. On the other side, you have independent analysts, some credentialed, some not, some rigorous, some reckless. They lean into what doesn't fit cleanly. They bring the anomalies forward. They magnify the questions. They invite people into the uncertainty, because uncertainty is where curiosity lives. And curiosity keeps audiences engaged. But that's also where the incentives can warp the message. Mystery sells. A careful maybe doesn't travel as far as a confident what if. And here's the uncomfortable truth: neither style is purely honest. NASA's certainty is partly a performance, not because there's a conspiracy, but because institutions are built to project stability. Behind the scenes, scientists argue, they disagree. They write papers exploring edge cases. They test weird explanations because that's what you do when the data refuses to sit still. Yet the public-facing version often sounds like the debate is already over. Don't worry, it's just a comet. Meanwhile, some independent coverage pushes probability estimates as if they're hard facts, when they're really conditional models, numbers that depend on assumptions. Independence claims, and a sample size that's still laughably small. The anomalies are real. Yes, but real anomalies is not the same thing as proof of technology. When you oversell that leap, you don't strengthen the case. You weaken the public's ability to understand what the science actually says. So the truth sits in the middle. Where it usually does, 3i Atlas is stranger than the official messaging tends to admit, and far less certainly artificial than the loudest voices imply. It is not nothing. It is not case closed. But it is also not a solved riddle pointing cleanly to a manufactured answer. What gets lost in the institutional versus independent shouting match is something far more important and far more inspiring. The amateurs aren't just spectators. They're participants. Backyard astronomers have captured features that the big institutions didn't highlight at first. Thousands of observers, spread across continents, have documented the evolution of the coma and tail structures night after night, exactly the kind of sustained, repetitive monitoring that professional observatories often can't afford because telescope time is scarce and priorities are endless, long before a press release is drafted. The sky keeps changing. The amateurs are simply there to notice. And this isn't new in principle. Amateur astronomers have helped comet science for decades, discovering new comets, tracking brightness, curves, reporting outbursts, monitoring fragmentation events. What's changed is the capability ceiling. The gear has evolved, the software has evolved, and the collective skill of online communities has evolved with it. Smart telescopes with automated tracking and stacking can now pull faint structure out of darkness in minutes. High-quality CCD and CMOS sensors capture subtle details that older photographic methods would have swallowed in noise. Processing workflows once limited to professionals are now shared openly, refined in public, improved weekly. The result is something that almost functions like a distributed instrument, a global network of eyes and lenses, creating an ongoing time-lapse of a moving target. And with 3i Atlas, that distributed instrument has delivered moments that even professionals admit are worth taking seriously. Between November 22nd and 24th, observers in Japan, Spain, and Chile photographed the object and produced strikingly consistent results. Their images showed a defined coma structure, a narrow tail extending over 600 miles, and what appeared, depending on interpretation, to be a conical geometry in the near-nucleus region. Avi Loeb circulated those images widely, emphasizing that they seemed to reveal more than the official NASA releases had conveyed. He pointed again to the anti-tail, still visible weeks after perihelion, as evidence of unusual dust dynamics. He highlighted the apparent order in the coma patterns that looked less like random outgassing and more like organized activity. Were those details genuine physical features, or were they the ghosts that sometimes appear when you push weak signals through aggressive stacking and enhancement? That question sits at the heart of observational astronomy at extreme esotame distances. The signal is faint. The noise is relentless. Every tool we use to extract detail stacking, sharpening, contrast, stretching can also manufacture illusions if you're not careful. Distinguishing structure from artifact requires skepticism, expertise, and something even more valuable, independent replication. And in this case, replication is exactly what makes the story different. When a feature shows up in one processed frame, you shrug. When it shows up across multiple nights, across different equipment, across different observers, across different continents, you pay attention. That's why certain elements have moved out of the maybe category and into the real feature category. The spiral jet structures have been seen repeatedly. The anti-tail has been confirmed. The dual tail geometry visible in the JUICE teaser image has a perfectly normal physical interpretation and aligns with what comets often display when conditions are right. What remains contested is not whether these features exist, it's what they mean. The institutional conclusion remains consistent: NASA, ESA, and the overwhelming majority of professional astronomers describe 3i Atlas as an unusual but natural interstellar comet, with oddities explainable through unfamiliar composition, long interstellar aging, and the diversity of comet behavior we already know exists. The minority view, championed most visibly by Loeb, and entertained by a smaller number of others, argues that the pile-up of anomalies warrants serious consideration of a technological hypothesis. Not certainty, not a declaration, but a refusal to rule it out prematurely. Both positions can be argued. Both might still be wrong. And that's precisely why the one unacceptable posture is the one that tries to end the conversation by force. Because refusing to look is not science. Declaring certainty while questions remain is not science. Dismissing curiosity because the implications might be uncomfortable is not science. The amateurs understand that instinctively. They observe because they can. They share because they want the truth more than they want to win. They question because questioning is how the universe gets decoded. As December 19th, 2025 approaches, the temperature of this debate will rise. More images will surface. More analyses will appear. Some anomalies will likely soften under better data. Others may sharpen. That's the nature of real discovery. It doesn't move in a straight line. But one outcome is already irreversible regardless of what 3i Atlas ultimately proves to be. The wall between professional and amateur astronomy has never been thinner. Ordinary people can now contribute meaningfully to extraordinary events. And when official channels communicate poorly, the public no longer has to wait in silence. There are other eyes on the sky. And yet, beyond the noise, beyond the arguments about blur and processing and tone, one question keeps standing up again and again, because it's the reason millions are following this story at all. Is 3i Atlas simply a comet from another star? Or could it be something that has learned how to wear a comet's mask? The so-called mothership hypothesis has been labeled ridiculous, irresponsible, unscientific, and also, by others, provocative, necessary, overdue. But no matter what you call it, you cannot honestly call it resolved. The evidence that would decisively confirm it has not appeared. The evidence that would decisively destroy it has not arrived either. We are stuck in the most uncomfortable place of all, the middle ground where certainty is impossible, and the stakes are too captivating to ignore. So let's put it on trial properly. Not with vibes, not with fear, not with blind trust in institutions or blind distrust of them, with the only thing that matters: what the object does, what the data shows, and what reality is willing to reveal. And to do that, we need to start with the mainstream position, because it's mainstream for a reason. Most scientists believe 3i Atlas is a comet, not because they lack imagination, but because the baseline evidence points there. It has a coma. It has tails. It is outgassing water and carbon dioxide. Most researchers still default to the simplest explanation. 3i Atlas is a natural interstellar comet, unusual. Yes, but ultimately part of nature's vast menu of weirdness. And that's why Avi Loeb's mothership suggestion lands like a spark in dry grass. It runs against the gravitational pull of professional consensus. That doesn't automatically make it wrong. Consensus has been embarrassed before, but it does mean the standard of evidence changes. When you propose an extraordinary cause, you inherit an extraordinary burden. So let's treat the mothership hypothesis like a real claim, not a meme, not a punchline, not a belief system. What would it imply if 3i Atlas were artificial? What kind of evidence would support that conclusion? And what would strongly push us back toward just a comet, even if it's a comet with bad manners? At the heart of Loeb's argument is probability, not imagination. He looks at the pile of anomalies: orbital geometry, chemical oddities, polarization extremes, persistent anti-tail behavior, spiral jets, non-gravitational acceleration patterns, and he asks a statistical question: how likely is it that a single natural object would carry so many rare properties at once? His method is straightforward in concept. Assign a rough likelihood to each anomaly occurring in an ordinary natural scenario. Then combine them. If anomaly A is 1 inch 100, and anomaly B is 1 inch 100, and they're truly independent, then seeing both together starts to look like 1 inch 10. Ling ling ling. Multiply enough of those together, and you land in absurdly tiny numbers that feel like a warning flare. That style of reasoning isn't fringe. It's used in mainstream physics all the time. Particle physicists don't see a new particle the way you see a bird. They see a deviation in data, an excess of events above background, and they quantify how often random noise could imitate that excess. When that probability drops below a conventional threshold, the community calls it a discovery. But the logic has traps. Big ones. For Loeb's multiplication to be meaningful, two things must be true. First, the anomalies must be genuinely independent. If one oddity increases the chance of another, then multiplying them exaggerates rarity. A weird composition could plausibly cause weird outgassing behavior, which could plausibly affect brightness curves, tail morphology, and even non-gravitational acceleration. Correlation collapses the effective count of independent anomalies. Second, the baseline probabilities must be estimated correctly. And this is where the floor gets slippery. We have exactly 3 confirmed interstellar visitors in recorded history. We do not know the true distribution of their compositions, surface textures, and behaviors. If we don't know how often interstellar comets are nickel-rich or how often they show extreme polarization, then assigning 1-inch 100 is, at best, an educated guess. Critics hammer Loeb on these points, and they're not wrong to do it. If the anomalies are correlated and the priors are uncertain, the combined probability can become more storytelling than science. But criticism isn't the same as dismissal. Even after you reduce the math to something more conservative, accounting for correlations, widening uncertainties 3, IATLAS still looks like an outlier. The real disagreement is not, are there anomalies? The disagreement is whether the anomalies are suspicious enough to justify putting an artificial hypothesis on the table as a live contender, rather than as a rhetorical stunt. Now, if we take the artificial scenario seriously, we should take it seriously in a way that's strategically realistic, not Hollywood realistic. Most science fiction imagines obvious spacecraft metallic symmetry, glowing engines, crisp geometry. But an advanced civilization capable of interstellar travel might not advertise itself like a parade float. It might not share our aesthetics. More importantly, it might have reasons to avoid detection. That's where the Trojan horse version of the hypothesis comes in. Not alien mothership as a dramatic object broadcasting its presence, but a probe that camouflages itself as a natural body ice. Dust, rock, comet-like behavior. The perfect cover story. Slip through foreign systems quietly. Observe without being observed. If you don't know what kinds of civilizations you'll encounter, or whether they shoot first, stealth stops being a fantasy and becomes a rational design principle. In that framing, the anomalies would be interpreted as imperfect mimicry, a technological object attempting to pass as a comet, but leaving subtle fingerprints, chemistry that feels off, activity patterns that look too organized, jets that behave more like controlled venting than chaotic outgassing, not because it wants to be seen, but because perfect deception is hard. And yet, the same list of oddities can be read the opposite way, not imperfect mimicry. But the diversity of natural comets is broader than our models. Both interpretations can sit on the same data. That's the problem. So how do we distinguish between them? The gold standard would be unmistakably artificial behavior, something nature simply doesn't do. A trajectory change that cannot be explained by outgassing or gravity would be the cleanest. If 3I Atlas performed a sustained maneuver, accelerating in a way that violates conservation of momentum for a passive body, then the argument would end overnight. Artificial light emission would also be decisive. A coherent beam, structured pulses, or spectral signatures incompatible with reflection, fluorescence, or thermal processes. Radio transmissions, especially narrowband signals, tied directly to the object's position, would be powerful evidence. The release of subprobes, objects separating and maneuvering, would be extraordinary. So far, we have none of that. The Meerkat radio telescope in South Africa has already searched for narrowband signals. The result was null, no detected transmissions, with an upper limit roughly comparable at that distance to the power output of a mobile phone. The trajectory has remained consistent with gravitational dynamics plus comet-style outgassing. No course corrections, no hard turns, no unmistakable propulsion signature, no glowing patterns in the dark, no smoking gun. By those tests, 3. Atlas behaves like something nature can plausibly produce. But then comes the trap Loeb's critics hate most. Absence of evidence is not evidence of absence. A stealth probe would avoid radio leakage. It would avoid obvious maneuvers. It would avoid anything that screams technology, if it's designed not to be caught. The very lack of hard evidence can be reframed as consistent with the hypothesis. That's not because the hypothesis is strong, it's because it risks becoming unfalsifiable. And unfalsifiable ideas are where science starts to suffocate. This is the epistemological vice grip of the Trojan horse concept. We can prove artificial instantly if it acts artificial, but we can never prove natural with the same absolute confidence, because a sufficiently advanced technology could always hide behind natural behavior. The best we can do is weigh probabilities and ask what explanation requires the least strained assumptions. Loeb has publicly stated he assigns something like a 30–40% chance that 3I Atlas is not fully natural. That number is not a measurement. It's an informed personal judgment. Many scientists would put the probability far lower, some effectively at zero. The spread tells you something important. We're not arguing over a single fact. We're arguing over how to interpret incomplete data under uncertainty. But the most revealing part of this entire debate might not be the comet. It might be the culture. Loeb has taken heat that goes far beyond normal academic disagreement. People have called the hypothesis ridiculous, irresponsible, embarrassing. Some of that backlash is professional. He uses media attention aggressively. And many academics reflexively distrust anything that becomes a headline. Some of it is defensive. Researchers in astrobiology and exoplanet science worry sensational claims poison the well, threatening funding, credibility, and public trust. And some of it is simply human. The idea of alien technology in our solar system is psychologically destabilizing. It forces questions about security, religion, identity, and our place in the hierarchy of minds. When a possibility is unsettling, ridicule becomes a convenient sedative. The consequence is a social gradient inside science. Certain questions are safe, others are career toxic. Loeb can afford controversy because he has tenure at Harvard. Early career scientists watch how he's treated and quietly learn the lesson. Stay inside the fence. Don't touch the electric wire. Don't risk being labeled the person who goes there. And that matters no matter what 3I Atlas turns out to be. Because science advances by interrogating assumptions. If social pressure makes some questions taboo, even temporarily progress slows. Curiosity becomes selective. And the universe doesn't reward selective curiosity. It rewards whoever is willing to test the uncomfortable possibility properly, without turning it into a religion, and without banning it like a heresy. Here's the thought experiment that makes this clear. Suppose 3I Atlas is completely natural, just a rare, messy, volatile-rich interstellar comet with weird dust dynamics and unusual surface properties after billions of years in deep freeze. In that case, the mothership hypothesis is wrong, but asking the question still had value. It forced observers to watch more closely. It forced modelers to justify their assumptions. It forced institutions to confront how their messaging can backfire. It pulled public attention into the real texture of science uncertainty. Debate, competing interpretations, evidence that arrives in fragments, and if, on the other hand, the hypothesis is not wrong, if there is even a small technological component hiding under the ice, then the cost of dismissing the question too early would be historic. So the only intellectually honest posture is neither panic nor dismissal. It's disciplined curiosity. And disciplined curiosity demands a next step, not more arguments, but clearer criteria. What specific observations over the next window, especially around December 19th, 2025, would increase or decrease the plausibility of the mothership hypothesis in a way both sides would respect? Because if we can't agree on what would change our minds, we're not doing science anymore. We're doing theatre. And the universe doesn't care about theatre. It only responds to measurement. Now imagine, for a moment, that Loeb is right and 3I Atlas is artificial. In that scenario, the dismissive reflex from mainstream science doesn't just look cautious, it looks tragically short-sighted. We would have had a technological visitor in our own solar system and talked ourselves out of even considering it because the idea felt socially radioactive. That's the nightmare version of this story, not aliens, but our own intellectual self-censorship. And this is where the argument stops being about belief and starts being about decision-making. Even if the probability of artificial origin is low, The expected value of taking the hypothesis seriously is enormous. If 3I Atlas is natural and we investigate it as if it might be artificial, the worst-case outcome is what? A little embarrassment, some bruised egos, a few headlines aging poorly. But if 3I Atlas is artificial and we don't investigate it with maximum rigor because we were too comfortable to look, then we miss the single most important discovery in human history. Not a paper, not a prize, a rewrite of reality. That asymmetry is why I refuse to accept institutional reassurance as a substitute for inquiry. Not because I'm convinced it's alien, not because I have a secret dataset NASA doesn't, but because the stakes make lazy certainty irresponsible. We should watch, measure, question, keep one foot planted in skepticism and the other in humility, open to surprise, but allergic to wishful thinking. And there's another layer to this, one that's almost uncomfortable to admit, whatever 3I Atlas turns out to be. The way we've reacted to it has already exposed something real about us, about how institutions try to contain uncertainty, about how the public fills informational vacuums with story, about how scientists, human beings, not machines, navigate reputation, ridicule, and the fear of being wrong in public. That's why December 19th, 2025 feels charged. Not because it's a doomsday date, it's not, but because it's a deadline. After that closest approach, the object recedes, and the quality of the measurements decays with distance. The best window closes, and somewhere in the backlog of unprocessed data, spacecraft files waiting on downlinks, raw frames waiting on calibration, there may already be answers none of us have thought to ask for yet. But before we get to that crescendo, there's a quieter clue we have to confront. Not a measurement that screams, an absence that whispers, because silence is not nothing. Silence is information. It's a constraint. It's a boundary line drawn around the possibilities. And in the case of 3I Atlas, the silence we've detected, or more precisely, the silence we haven't been able to break, lives in the radio spectrum. What the radio silence really means. On November 5th, ScienceForSleep, one of the most sensitive radio observatories on Earth, aimed itself at an interstellar visitor and listened with intent. Meerkat in South Africa, 64 dishes spread across the Karoo Desert, locked onto 3I Atlas and searched for what SETI researchers call technosignatures, narrowband radio emissions that nature almost never produces. The kind of signal that implies engineering, a carrier tone, a tightly confined frequency spike, a beacon, intentional or accidental leaking from technology. They didn't find it, or more accurately, they found 689 signals, and every one of them traced back to us. Human-made radio frequency interference, terrestrial transmissions, satellite reflections, the messy echo of Earth talking to itself and mistaking the echo for a stranger's voice. Strip all of that away, and what remained was cosmic background hush, the faint static of the universe, the occasional astrophysical chirp. Nothing that could be credibly attributed to 3I Atlas. The sensitivity threshold matters here, because it turns nothing into something we can interpret. At the time of observation, 3I Atlas was about 334 million kilometers away. Meerkat's limit was so strong that if the object had been broadcasting in the 900 to 1,670 megahertz's range at roughly the power of a mobile phone around 1 watt, the array would have detected it. That's not a poetic metaphor. That's a brutal technical constraint. Detecting a 1 watt signal across that distance is like identifying a pinprick of engineered order inside a storm of noise. So what does that silence mean? Interpretation 1, the simplest and most likely. The straightforward reading is exactly what mainstream scientists would say. There is no transmitter because there is nothing to transmit. Comets do not run radios. Natural bodies are radio quiet, apart from thermal emission and certain molecular lines. If 3I Atlas is a comet, radio silence is not surprising, it's expected. Interpretation 2, silent does not equal non-technological, but silence is not a verdict. It's a boundary around a specific set of assumptions. Meerkat listened in a specific frequency window. It listened during specific times. It looked for narrowband signatures, the classic SETI-style footprint. If an advanced probe were present, it might not use those frequencies at all. It might communicate with tight beams aimed nowhere near Earth. It might use spread spectrum methods that blend into noise. It might transmit in optical or infrared lasers rather than radio. Or it might be deliberately passive, no active signaling because signaling is how you get noticed. And if the Trojan horse idea is even conceptually on the table, then radio silence becomes ambiguous in a very particular way. It doesn't falsify the hypothesis, but it does eliminate the easiest version of it, the version where the mothership is casually broadcasting like a lighthouse. Interpretation 3. Silence as a pressure test on our expectations. There's also a psychological lesson hiding in this result. Many people expected that if it were artificial, it would announce itself. That assumption is deeply human. We imagine contact as communication. But exploration doesn't require announcement. Observation doesn't require conversation. A probe designed for reconnaissance might treat silence as a feature, not a failure. So the silence doesn't end the story, but it narrows it. It says if there is technology here, it is either not transmitting in that band, not transmitting at that time, not transmitting in a way we know how to detect, or not transmitting at all. And that brings us to the real tension. The most decisive evidence would be an unmistakable techno-signature. Yet the most plausible stealth strategy produces none, which means we're forced back to the uncomfortable middle ground where we can't prove aliens. But we also can't justify complacency while the anomaly stack remains unresolved. So the question becomes sharper. If radio isn't giving us the smoking gun, what would? Because the next 2 weeks leading to December 19th, 2025 aren't just about watching something pass by. They're about using the remaining time to design the best possible falsification tests. Not tests that confirm what we want to believe. Tests that corner reality. And the next place to corner it isn't in the radio band. It's in the light itself, spectra. Polarization. Time variability, where physics leaves fingerprints it can't easily fake. Whether the culprit is nature or design, there's a perfectly reasonable way to read the meerkat result that makes the whole debate feel almost boring. Comets don't broadcast. And normal comet physics doesn't generate the kind of narrowband needle in the haystack signals SETI hunts for. If that's the frame, then the meerkat null result is simply what you'd expect. No verdict. No drama. No decisive clue. But the moment you allow the technological hypothesis onto the table, even as a thought experiment, the same silence takes on a different texture. Because if 3I Atlas were a probe, we would have no right to assume it would behave like a human radio tower. A genuinely advanced reconnaissance platform might have every incentive to remain quiet. Stealth is the simplest reason. If you're sending an observer into an unfamiliar system, broadcasting is the opposite of intelligence. Radio is a flare in the dark. It advertises presence. It invites attention. A cautious designer would build something that can measure everything and announce nothing. And interstellar time adds an even colder possibility. 3I Atlas has been traveling for billions of years. The civilization that launched it could be gone. Its targets could have changed. The mission could be on autopilot. It might be programmed to stay dormant unless it detects a specific trigger signals worth responding to, or conditions that match a long-forgotten directive. Or it could be communicating with an extremely narrow beam aimed somewhere that isn't Earth toward a relay, toward the origin system, toward something we can't see. Then there's the engineering reality. Radio waves are not necessarily the best option for interstellar communication. They spread out, their power falling with the square of distance. A civilization that has solved interstellar travel might also have solved communication in ways we can barely model: optical lasers, neutrino beams, exotic modulation techniques, or methods we haven't invented. In that sense, our radio arrays could be as mismatched to their language as a butterfly net is to a Wi-Fi network. So the meerkat non-detection shrinks the hypothesis space, but it does not shut the door. That's the curse, and the discipline of SETI null results are inherently ambiguous. They can mean nobody is there. They can mean somebody is there but silent. They can mean somebody is talking, but not in a channel we're listening to. So, what would a positive detection even look like? The classic SETI gold standard is a strong, narrowband signal, a clean spike at a specific frequency that nature doesn't produce in that way. The hydrogen line at 1,420 MHz has long been favored for symbolic reasons. Hydrogen is universal. The line is prominent, and any radio-capable civilization would know it. Another often cited region is the so-called water hole, the quieter band between hydrogen and hydroxyl-related frequencies. People also talk about mathematically meaningful frequencies, multiples tied to constants, because they might communicate intentional design. But here's the inconvenient truth: the electromagnetic spectrum is vast, and we search it like we're sampling the ocean with a teaspoon. Meerkat's range 900 to 1,670 MHz is substantial and strategically chosen. Yet it still represents a sliver of what exists, and it leaves optical, infrared, and everything beyond entirely untouched. Other teams have looked too. Breakthrough Listen has directed resources toward 3i Atlas, and university groups have pointed instruments at it. So far, no confirmed techno-signatures. Again, not a verdict, just a boundary line drawn around what's been tested. Now there's an additional twist that makes this story more interesting than silence equals nothing. 3i Atlas is not actually silent in every way. It is outgassing. Water, carbon dioxide, and other volatiles are streaming into its coma under solar ultraviolet light. Some of those molecules break apart and produce radio-detectable species. And in fact, Meerkat's campaign didn't just establish limits on artificial narrowband emissions, it also reported hydroxyl OH associated with the comet, produced when escaping water is photodissociated by sunlight. That's a milestone, the first radio detection of a molecular species from an interstellar comet. And it is strongly consistent with ordinary cometary behavior. But notice what that does to the mothership debate. If 3i Atlas were a disguised probe, you'd expect it to imitate cometary outgassing convincingly. Water and OH would be part of that mask. So the OH detection supports the comet interpretation. But it doesn't logically eliminate the camouflage interpretation. A good disguise looks like the real thing. So what would separate a real comet from a fake one? Not a single molecule. Not even water present. The discriminators would be subtler. Molecular ratios that don't make geochemical sense, patterns that are hard to get from natural ice chemistry. Temporal modulation in spectral lines, regular, information-like patterns embedded in the emissions. Nature produces variability, but it rarely produces clean, repeatable encoding. Correlation between changes in outgassing and trajectory behavior that doesn't match known physics is. So far, none of that has been observed. The chemistry is unusual in places HICO too. Nickel oddities, but still plausibly natural, given how little we know about interstellar comet diversity. And that brings us to the deeper limitation: we don't fully know what we're looking for. We search for radio because we use radio. We search for narrowband spikes because our technology makes narrowband spikes. That's the streetlight effect in its purest form. We're looking where the tools illuminate, not necessarily where the keys would be. Loeb's argument is that the response shouldn't be resignation, it should be expansion. Broaden the search. Diversify the methods. Treat interstellar objects as high-value targets for technosignature screening, simply because the payoff is immense and the cost is modest. That logic has real merit. But it creates a parallel risk when you don't have a strong baseline model of what normal looks like. Every surprise becomes a potential signal, and with only 3 confirmed interstellar visitors, surprises are guaranteed. We're sampling a population with almost no statistics. Still, the Meerkat campaign did something vital. It gave us a flaw, a reference point. It tells us that if 3I Atlas is broadcasting in that band, it's doing so below the equivalent of a 1-watt phone at that distance, or it's not broadcasting toward us at all, which means the next steps are clear, and they're time-sensitive. As December 19th, 2025 approaches, additional radio observations can exploit the improved geometry and slightly improved sensitivity. The gain in distance terms is modest, but geometry matters. A narrow beam that missed Earth in early November might intersect our line of sight later, purely because the relative angles change. And then comes the next potential inflection point, March 2026, when 3I Atlas passes Jupiter. If there is any scenario, natural or artificial, where something dramatic happens, Jupiter is where you'd watch for it. A gravitational encounter can perturb a natural object. And if the more speculative mothership story were true, Jupiter is exactly the kind of place a craft might use for an Oberth-like maneuver, or where it might deploy subprobes, or change behavior in ways that are suddenly measurable. That doesn't mean it will happen, but it defines the next hard test. Not is it silent, but does it do anything at Jupiter that comets do not do, and can we catch it in time across radio, optical, infrared, and trajectory tracking? Because if silence is ambiguous, behavior is not. And the closer we get to those two dates, December 19th, 2025 and March 2026, the more the universe forces this story out of philosophy and into physics, where speculation either collapses or becomes evidence. That's the unnerving part about the Jupiter chapter. It doesn't belong to the comet watching phase of the story at all. It belongs to the part that happens after the peak attention fades, after the live streams end, after the headlines move on, after most people file 3I Atlas away as either mystery solved or mystery ignored, because the observation window doesn't close on December 19th. It only changes shape. Up to December 19th, the urgency is emotional and practical, closest approach, best geometry, the clearest chance to pin down brightness curves, tail morphology, and any last-minute surprises close enough to measure with confidence. But after that, the urgency becomes something colder: trajectory, the long arc, the part of the story where nothing dramatic is expected until it is. And this is where the radio silence takes on its true meaning, not as evidence for or against anything, but as proof that we've finally learned the right habit: coordinated attention. The most important result so far may not be a detection at all. It may be the simple fact that, for the first time in human history, an interstellar visitor has triggered a global response that includes professional observatories, amateur networks, space missions, trajectory analysts, and centigrade monitoring, everyone watching the same target in real time, with different tools, from different angles, asking uncomfortable questions without waiting for permission. If 3I Atlas is exactly what mainstream astronomy says it is, an ancient, unusually active interstellar comet, then that vigilance costs us almost nothing and returns an enormous scientific reward. We learn how alien ice behaves, how volatile inventories differ across star systems, how dust dynamics evolve under solar heating after eons in the deep freeze. And if it is something more, something rare enough that most people would rather dismiss it than sit with the possibility, then we don't lose the most important discovery in our species' history because we weren't paying attention. That is what the silence really tells us. Not nothing is there, but we are listening now. But before we get swept into the future, before we start talking about what the next interstellar visitor might bring, we have to deal with one piece of the present that refuses to sit still. Because 3I Atlas is not simply leaving in a clean, simple hyperbolic exit. Its path is taking it straight toward the gravitational throne room of the solar system. March 16th. Jupiter. And it isn't the fact of a Jupiter encounter that raises eyebrows. Interstellar trajectories are what they are: geometry and momentum, not intention. The unsettling part is the precision. Right now, as the orbital solutions tighten with every new data set, The best estimates place the closest approach at roughly 53 million kilometers. On its own, that's just a number. Jupiter is huge, space is huge, close passes happen. But then you compare it to Jupiter's Hill radius. The Hill radius is the boundary that marks where a planet's gravity becomes dominant enough to hold onto satellites against the Sun's pull. For Jupiter, orbiting the Sun, it's about 5 million kilometers, the edge of the planet's effective gravitational territory. And Dry Eye Atlas, by the current calculations, isn't merely passing near that boundary, it's threading it within about 60 km, roughly 1 part in 1,000. That is the coincidence Loeb highlighted, and he attaches a rough probability estimate about 1 inch 26,000 for hitting that specific distance by chance. Not impossible, not even astronomically impossible, but it's the kind of alignment that becomes psychologically heavy when it lands on top of a pile of other alignments, ecliptic proximity, a peculiar retrograde geometry, the sequence of planetary close approaches, the oddities in activity and morphology. Each one is survivable on its own. In a cluster, they begin to feel like a pattern even when they may not be. So why does the Hill radius matter operationally? Because if you wanted to use Jupiter as a tool, not as a destination, you'd care about the region where Jupiter's gravity can strongly sculpt trajectories without necessarily capturing you. Too far out, Jupiter's influence becomes a gentle nudge, measurable, but not decisive. Too deep in, the encounter becomes dangerous. You increase the risk of being captured, shattered, or forced into a chaotic path you can't control. But right near the edge, near the Hill boundary, you're in a sweet zone where a close pass can deliver a substantial gravitational deflection while preserving a clean exit. This is the core of what people mean when they talk about a Jupiter maneuver in this context. Not magic, not science fiction, just gravity used as leverage for a natural object. That leverage is passive. Jupiter will bend the trajectory according to mass, velocity, and distance, no intention required. For a technological object, if you allow that hypothesis even for a moment, the leverage becomes strategic. Jupiter becomes a place where you could alter your outbound direction toward a particular region of the sky. Change your speed relative to the Sun in a way that looks subtle unless you're tracking precisely to. Shed material natural debris, or in the extreme speculative case, something like subprobes under the cover of an already complex gravitational interaction. And here is the key point, the one that makes March 2026 more than an epilogue. Jupiter is where ambiguity can become measurable. Because the closer you get to a major gravitational encounter, the more predictive your models become and the more glaring any deviation will be. If 3I Atlas does nothing but behave like a comet, then the Jupiter pass will look like an elegant textbook curve, gravity plus outgassing, within tolerances. But if something about its motion begins to drift outside those tolerances, if the post-encounter path diverges in ways that don't match plausible jet-driven forces, then even skeptics will have to take notice. Not because anyone wants a technological explanation, but because orbital mechanics doesn't care what we want. That's what makes Anomaly 13 so haunting. It isn't the weirdest detail in the catalogue. It's the one that tells us the story still has a second act, one that plays out when the cameras are no longer pointed at the stage. And it forces a final, practical question. When March 16th, 2026 arrive, will we still be watching with the same intensity, running the same coordinated network of tracking, spectroscopy, radio monitoring, and amateur imaging? Or will we let the most diagnostic encounter of the entire trajectory happen in the quiet, after the world has moved on? Because if we've learned anything from 3I Atlas already, it's this: the universe doesn't schedule its revelations for our convenience, and Jupiter doesn't care whether we're paying attention. It will do what it always does, bend the path of whatever passes near. The only variable left is us. By the time we reach that Jupiter corridor, we will be dealing with a very different kind of object, at least in terms of visibility. Not because 3i Atlas will have changed identity, but because distance changes everything. Sunlight weakens, sublimation slows, the coma thins, the tales fade into a whisper. What is now a headline becomes, in practical terms, a faint moving target that only the largest instruments can hold. And yet, paradoxically, that is exactly what makes the March 2026 window so consequential, because the physics of a gravity-assist and Oberth maneuver, named for Hermann Oberth, is indifferent to publicity. It doesn't care whether the world is watching. Space agencies use gravity assists constantly. Voyager used Jupiter to sling outward. Juno used it as part of the choreography that ultimately let it settle into Jupiter's domain. The technique is so standard it's almost boring in mission design. But apply that same logic to an interstellar visitor, and the boring becomes loaded. A fast object on a hyperbolic path passing near Jupiter gets options, whether it intends to or not. Jupiter can bend the outbound trajectory, reshape the exit direction, slightly change the final speed relative to the Sun, and most intriguingly, from a strategic lens, provide a moment of gravitational complexity where small actions can hide inside a larger kata. Predictable curve. Now, let's say it plainly again. Because it matters, this is speculation. There is no evidence that 3i Atlas will do anything at Jupiter except fly past. Its path so far has obeyed the expected combination of gravity and comet-like outgassing. No clean smoking gun has appeared. The Hill radius coincidence may be nothing more than cosmic luck. But speculation has a purpose here, not to sell fantasy, but to clarify what counts as a testable idea. If you're trying to distinguish unusual comet from something more, the most useful moments are the ones where the universe itself provides a natural experiment. And Jupiter is exactly that. Why Jupiter is a built-in experiment. Jupiter isn't just massive. It is electrically alive. Its magnetosphere is the largest structure in the solar system after the heliosphere. A rotating powerhouse filled with charged particles, plasma currents, and magnetic fields strong enough to sculpt the environment around it like weather. If 3i Atlas passes within roughly 53 million kms, the same neighborhood as Jupiter's Hill sphere, then its ionized coma will enter a region where those charged particles and magnetic lines of force can interact with cometary ions in ways that are measurable. That interaction can reveal things we normally struggle to infer from far away: how much gas is being produced, what kinds of ions dominate these, how quickly material is being stripped away, how the comet's plasma tail behaves under extreme magnetic forcing. In other words, Jupiter can act like a stress test, a place where ordinary comet physics becomes louder, not quieter, because the environment is more intense. And if something about 3i Atlas is not ordinary, that's where the difference may become easiest to spot: the Juno angle. This is why Juno, already orbiting Jupiter, matters so much. Juno was built to study Jupiter's interior, atmosphere, auroras, and magnetic field, not to chase comets. But the last few months have shown a pattern: missions not designed for this story keep becoming part of it. Mars orbiters weren't comet cameras, yet they delivered trajectory refinements. JUICE wasn't a comet observer, yet it gave us an off-Earth perspective and a teaser image that reignited debate. Juno could do the same, not with Hollywood close-ups, nothing like that, but with context that Earth-based telescopes can't provide in situ measurements of the environment 3i Atlas will pass through, plus remote observations from a vantage point near the encounter. Even if Juno only contributes partial data, it would still be scientifically precious, because it would anchor the encounter in real measurements rather than pure modeling. And here's the uncomfortable part: by March 2026, the object will likely be around magnitude 15 or fainter. That's beyond almost all amateur capability. The vast global distributed telescope of backyard observers that has documented the tails and jet structures through December will go quiet, not from lack of interest, but from physics. It will simply be too faint, which means the monitoring burden shifts back onto professional facilities. The monitoring gap problem. This is the risk Loeb has been warning about, not that a maneuver is likely, but that if something odd were to happen when the object is faint and far and culturally forgotten, the odds of someone noticing drop sharply, and his Trojan horse delay scenario again. Speculative depends on exactly that human weakness. If you were designing stealth, you wouldn't reveal anything during the high attention phase when every telescope is pointed at you. You would wait until the target audience is tired, distracted, and looking elsewhere. You would wait until the object has faded into the outer system, where observation time is expensive and public interest has evaporated. Is that what's happening? Probably not. But the logic is clean enough that it creates a responsible question. Will we keep tracking anyway? Because the cost of tracking is finite, and the payoff, either way, is enormous. If it's natural, we learn how interstellar comet activity behaves at large heliocentric distances and in a giant planet environment. If it's not, March 2026 is one of the only remaining windows where not might become visible. The calendar of what comes next. Here's the timeline as it stands. December 19th. 2025 remains the best near-term opportunity for precision tracking, imaging, and public participation. February 2026 is when the bulk of the JUICE data from its November observations is expected to finally reach Earth face, delayed by the communications constraints while the high-gain antenna is used as a heat shield. March 16th, 2026 is the Jupiter encounter, roughly 53 million km8, strikingly close to Jupiter's Hill radius. 2031 is when JUICE actually arrives at Jupiter. Far too late to witness the 2026 flyby directly, but still relevant because the mission's existence underscores how valuable Jupiter system perspectives can be. Meanwhile, the scientific digestion of what we already have will stretch on for years. JWST spectra, Hubble reobservations, ALMA constraints, light curves, polarimetry, and the messy, invaluable archive of amateur imaging that will need calibration and careful cross-comparison to separate real structures from processing artifacts. And that's important to emphasize. Understanding doesn't arrive all at once. It arrives in layers, first the observation, then the argument, then the slow narrowing of what's plausible. Some anomalies will collapse into mundane explanations. Some will remain stubborn. A few might sharpen into genuine puzzles. And that is why the story is not ending at closest approach. It is simply moving from the bright, dramatic phase into the quiet, forensic phase, where the most meaningful details can emerge precisely because fewer people are watching. So, the question becomes practical again. What do we need to collect between now and December 19th that will still matter when 3i Atlas is a faint speck near Jupiter? Because the better our baseline measurements are, activity rates, dust properties, tail morphology, rotation signatures, the easier it becomes to recognize change later. And that brings us back to the immediate window in front of us, the final days before closest approach, when the object is still active enough to show us its personality clearly, and still close enough that subtle doesn't automatically mean invisible. Next, we need to focus on what the best observers are watching for right now. What changes would be normal? What changes would be surprising? And which signatures, if they appear, would move this story out of the realm of debate and into the realm of undeniable fact? And that is the nightmare scenario some researchers quietly game out in private, not because they think it's likely, but because they understand how unforgiving the geometry is. If the March 2026 Jupiter encounter were to produce something that cannot be explained by natural physics, an unmistakable maneuver, the deliberate release of smaller objects, an organized pattern of activity that no comet can plausibly generate, then by the time we realize what we're seeing, it will already be too late in the only way that matters, because distance is a lock. By March, 3i Atlas will be billions of kilometers away, receding fast, fading hard, and moving through a part of the solar system where even large telescopes are fighting for photons. There would be no dramatic pivot, No emergency mission. No second pass. No, let's take another look. Whatever we learn the way astronomers always learn from light. Already old by the time it reaches us. Carrying information we can analyze but not touch. We would have the most profound confirmation imaginable evidence of technology from another civilization, and we would also have to watch it disappear into interstellar darkness, carrying the deeper answers with it. A cosmic door cracking open for a heartbeat, and then slamming shut. That single possibility remote, but emotionally radioactive is why the idea of an interceptor mission has started circulating with more urgency than it did before 3I Atlas. Not as a reaction to this object specifically, because this object is already gone in practical terms. Even our fastest craft can't chase it. The Parker Solar Probe can hit around 430 miles per hour near perihelion. Yes, but that number is deceptive. It reaches those speeds by falling deep into the sun's gravity well, and it still doesn't translate into a simple catch-up capability for an object that is already outbound, moving at roughly 150 miles per hour and drawing away on an escape trajectory. 3I Atlas is not an interception problem. It's a lesson. If we ever want a real rendezvous with an interstellar visitor, we need a different class of propulsion and a different posture entirely readiness. Of not improvisation. Concepts exist on paper laser-driven solar sails, advanced nuclear propulsion, hybrid architectures designed to launch quickly and accelerate continuously. None of this is operational today. But the gap is not mystical. It's engineering, budgets, time, and political will. And that may be the most permanent legacy of the 3I Atlas event. It exposed how unprepared we are. We had months, not years. We had curiosity, not infrastructure. We had telescopes, but no real ability to close the distance. If the universe ever drops something truly extraordinary into our neighborhood, and not just odd, but world-changing, we could easily end up doing exactly what we are doing now, watching, recording, arguing, and then waving goodbye to the most important object we've ever encountered. The universe doesn't schedule its surprises around our capabilities. It doesn't wait until we have a launch window and a committee and a plan. It delivers what it delivers, on the trajectories that gravity dictates, and it leaves when physics says it must leave. We are observers, privileged, intelligent, and often helpless in the most literal sense. So, what can we do? We can watch without flinching. We can record with discipline. We can treat uncertainty as a responsibility, not an embarrassment. And we can stop confusing reassuring with true. Not because we should panic, 3I Atlas poses no danger, but because the adult posture toward the unknown is not denial. It is attention. Which brings us back to the clock. As of this recording, December 19th is 14 days away, the closest approach. The brightest point in the arc. The best chance we will ever get to wring meaning out of the light before the object fades into the long, outbound night. After that, the slow dimming, the careful tracking, the March 2026, Jupiter passage, and then the inevitable thinning of signal until, one day, there is only empty sky where a visitor used to be, unless it surprises us, unless the universe adds one last twist before the chapter closes. So yes, the countdown continues. 14 days to prepare. 14 days to pay attention. 14 days to treat this moment like what it is, a once-only intersection of paths across unimaginable scales of time. And in those 14 days, there's one final question that matters as much as any spectral line or trajectory plot. Not what is 3I Atlas we are trying. Honestly, to answer that, the deeper question is, what does our response say about us? Because whether anyone is listening or not, we are broadcasting something into the universe with our behavior. Not in radio waves. Necessarily, though, that too, but in the way we handle mystery. In whether we choose curiosity over comfort, rigor over reflex, openness over ridicule, December 19th, and the message in a bottle. If the thick disk estimate is even roughly correct, then 3I Atlas may have been traveling for 7 billion years longer than the Sun has existed. That number is so large it becomes almost meaningless until you anchor it against things you can feel. Our star is about 6 billion years old, which means, in that scenario, 3I Atlas was already ancient before the first light ever rose in this system, before Earth's crust cooled, before oceans, before life, before bacteria, before everything we've ever dug up, named, measured, or mythologized. Every mountain you've stood on came later. Every fossil, every city, every empire, every satellite, every human story came later. This object, if the estimates are right, was already out there wandering the Milky Way while our planet didn't yet exist as a concept. And now, absurdly, it intersects us for a few months. A cosmic coincidence so precise it feels authored, even when we know it isn't. A crossing of trajectories across distances and timescales that dwarf the entire human narrative into something smaller than a blink. We get to see it. We get to study it. We get to ask what it is, where it came from, and what it might mean. That is the privilege of being alive right now, not simply to witness an interstellar visitor, but to witness the third confirmed one, the most active, the most debated, the one that has dragged theoretical questions down into the realm of practical urgency. Because once you admit that interstellar objects can arrive once you see them with your own eyes, once you plot their paths, once you measure their outgassing, once you watch the arguments fracture into competing interpretations, you can't unlearn the implication. The space between stars is not an empty hallway. It's a road, and sometimes something comes down it. So the message in a bottle isn't just the comet itself. It's the fact that we are capable of recognizing the bottle at all, of turning instruments toward it, of disagreeing intelligently, of staying awake before dawn and chasing a faint smear of light because the meaning matters to us. And that is what makes December 19th feel bigger than a date on a calendar. It's a test of attention, a test of humility, a test of whether we can face the unknown without turning it into either a fairy tale or a press release. Because when 3I Atlas finally passes and begins its long retreat toward Jupiter, the universe will not grade us on whether we guessed comet or probe. The universe will simply continue being what it is, vast, indifferent, and full of surprises. The question is whether we will continue being what we are at our best, curious, careful, unafraid to look, and ready if the bottle ever contains something we never expected to find. Are we alone? Is the space between stars nothing but the shed-off rubble of dead worlds, ice, rock, dust, the leftovers of formation and collision? Or could there be something more deliberate moving through the same dark lanes of the galaxy? Something designed, not merely thrown. Those questions existed long before 3I Atlas. They'll still be here long after it's gone, but for a brief window measured in weeks, not centuries. They stopped being distant philosophy and became something practical, something measurable, something you can point a telescope at. Because this time, we're not arguing about a hypothetical signal from a hypothetical star. We're searching for techno-signatures in a real object with a real trajectory that really did arrive from another system. That fact alone is extraordinary, no matter what the final explanation turns out to be. Now picture December 19th. The sun rises like it always does, unmoved by the drama playing out hundreds of millions of miles away. People make coffee. Commutes happen. Arguments unfold. Feeds refresh. Most of the world lives an ordinary day, unaware that a relic from another star system is sliding past our neighborhood. But for the people who know, the day carries a different weight. Not a weight of fear, this is not a threat, but a kind of quiet gravity. The sensation that the universe is doing something rare in front of us. And we are lucky enough to be paying attention. In observatories around the world, professionals will already be at their instruments. The virtual telescope project in Italy will be streaming live. Facilities in Hawaii, Chile, Australia, and the Canary Islands will be collecting data. And across countless backyards, cold breath, stiff fingers, dew forming on equipment, amateur astronomers will be aiming at Leo, searching for a faint, ghostly blur beneath Regulus. Above it all, far beyond Earth's atmosphere, the instruments we built as extensions of our senses will be doing what they do best. Hubble, still working after decades, gathering photons that will be examined and re-examined for years. James Webb, floating near L2, turning that golden mirror towards something that did not form here. Spacecraft scattered across the inner solar system, cameras and spectrometers and sensors quietly taking their turn in a coordinated watch. From Earth, from orbit, from Mars's vicinity, from distant vantage points that only machines can occupy. Eyes, electronic and human tracking, an object reaching its closest point to us at roughly 1.8 astronomical units, about 270 million kilometers, nearly twice the Earth-Sun distance. Not close in the way people imagine when they hear the word. If 3I Atlas were visible to the naked eye, it would be just another faint point swallowed by the crowded sky. But in cosmic terms, this is a near miss. A traveler that has crossed billions of years and incomprehensible distances is passing within what feels like shouting range, astronomically speaking, and then it keeps going. And that is the part that tightens the throat when you really let it sink in. The impermanence. 3I Atlas does not stop for us. It does not slow down because we're curious. It does not wait for consensus, or better instruments, or the political will to launch something that could catch it. It comes. It passes. It leaves. By January, it will already be dimmer. By March, only the largest professional instruments will comfortably track it as it approaches Jupiter. By summer, it will be fading toward the edge of detectability. And within a few years, it will be gone, an outbound trajectory, a thinning signal, and then empty coordinates where a visitor used to be. A data set, a memory, a mystery that may never fully resolve. So, what will we have learned? No matter which side of the debate you lean toward, we will have learned that interstellar objects are not mythical. The fact that we've confirmed 3 in a short span after all of human history had none suggests we were never seeing them because we weren't looking well enough. With the Vera Rubin Observatory coming online, this won't be a once-in-a-lifetime story. This will be the beginning of a new era. More will come. We will have learned that chemistry travels. Water, carbon dioxide, familiar volatiles, signatures that look like cousins of our own solar system's frozen bodies, hint that the ingredients of planetary systems are not unique to our neighborhood. The same raw materials that built our comets and outer worlds appear to exist elsewhere. 2. We will have learned that objects can survive the deep freeze of interstellar space for immense spans of time and still wake up when they meet a star. The cryovolcanic-style activity and organized jets, whatever their ultimate interpretation, underline a simple truth. Ancient ice can keep its secrets locked away until heat and sunlight pry them loose. We will have learned how to coordinate globally, in real time despite shutdowns, institutional friction, and disagreements about narrative. The response to 3I Atlas has been messy, human, imperfect, and still remarkable. Next time, we will react faster, we will share better, we will be more prepared, and we will have learned something about ourselves, about how quickly wonder can turn into paranoia, about how hunger for meaning can distort pattern recognition, about how institutions try to project calm even when the private conversation is full of question marks, about how ordinary people, armed with smart telescopes, CCD cameras, and online collaboration, can now contribute real observations that shape the professional discussion. The debate will not end on December 19th. It won't end when the comet fades from view. It may echo for years, maybe decades, because the anomalies catalogued around it will either be explained one by one, or they will remain as stubborn knots in the record, fueling new models, new arguments, new cautionary lessons about certainty. Some people will remember 3I Atlas as the moment they became convinced we are not alone because the coincidences felt too sharp, the patterns too insistent, the presence too difficult to shrug off. Others will remember it as a masterclass in how strange nature can look when you only have a few examples, how an unusual comet can mimic intention if you're primed to see design everywhere, and how disciplined skepticism matters most when the alternative is emotionally irresistible. Both memories will shape how we respond to the next visitor. And there will be a next visitor. Maybe it will be utterly ordinary, a textbook object, easy to classify. Maybe it will be stranger than this one, faster, darker, quieter, harder to interpret. Maybe one day something will arrive that doesn't just provoke debate, but forces resolution. Until then, the universe remains what it has always been: vast, old, indifferent to our theories, and unapologetically capable of surprising us. It might be teeming with intelligence, or it might be a cosmic desert and we are the only minds staring up, asking the question. We don't know. We might never know in the clean, cinematic way people crave, but we can keep doing the one thing that gives us any chance at all. We can look, we can listen, we can build better tools. We can keep our standards high without closing our minds. 3I Atlas is leaving. Whatever it is leaving. And we have to let it go physically, but we do not have to let go of what it taught us. We can carry the questions forward. We can carry the discipline forward. We can carry the humility forward. Because the universe doesn't send messages in sentences. It sends them in objects, anomalies, events, phenomena that punch holes in our assumptions and force us to revise the map. 3I Atlas is one of those messages, a bottle from a distant shore, washing up on our cosmic beach after billions of years at sea. Maybe we never fully translate it. Maybe we only learn a few words, but we can still hold it up to the light, turn it slowly, examine every surface, and wonder honestly who sent it and why. And that is more than enough. It is the privilege of consciousness in a universe that mostly does not have any. So as December 19th approaches, keep your eyes on Leo. Keep your mind open. Keep your standards strict. And keep your wonder intact. Because whether the answer is a comet or something else, this much is already true. The cosmos reached into our neighborhood and gave us a reason to pay attention. Clear skies wherever you are.